The story of Saturn begins in the quiet boundary between sunlight and deep space, where a pale, distant world orbits with slow precision. From this vantage point, Saturn does not appear dramatic or imposing. Instead, it presents itself as a soft, muted presence. A planet defined by gentle colors, stable motion, and a rhythmic cycle shaped over billions of years. This calm entry point, supported by decades of observation from ground-based telescopes and deep space missions, allows the viewer to settle into the narrative with a sense of quiet immersion. Saturn's realm becomes not a spectacle, but a place to be explored with patient attention. Viewed through even a modest telescope, Saturn appears as a bright, steady disk, its ring system forming a clean geometric outline around the planet. Astronomical records from the 17th century describe this first impression as striking not because of intensity, but because of clarity. Modern measurements confirm that Saturn's light is unusually stable in the night sky, a result of its high reflectivity and distance from the Sun. Observations from the Hubble Space Telescope show that this stability enables precise monitoring of Saturn's atmosphere over long periods, revealing slow-moving patterns rather than sudden changes. The planet's visual consistency offers a natural entry into the calm observational tone that frames this documentary. Saturn's distance from the Sun, an average of 1.4 billion kilometers, places it within the colder outer region of the solar system. At this location, sunlight arrives at only about one of the intensity felt on Earth. This low-energy environment shapes every aspect of the Saturnian system. Atmospheric dynamics progress gradually, cloud features evolve slowly, and temperature gradients remain gentle across wide latitudes. Data from the Cassini spacecraft confirmed that these environmental conditions produce a planet dominated by long-lived weather structures, including stable jet streams and repeating hexagonal flows at the North Pole. These findings support the broader scientific insight that environments with limited solar input naturally cultivate slow, sustained planetary processes. The rings, from a far-off vantage, appear as a thin, uniform band encircling the planet. Early astronomers described them as handles or ears, unable to resolve their true shape with early optics. Today, high-resolution imaging from Hubble and Cassini reveals that the rings are composed of countless particles ranging in size from fine dust to large icy fragments. Their collective motion creates the smooth appearance that telescopes record from Earth. This observational simplicity contrasts with the underlying complexity, offering the first interpretive insight of this chapter. In the Saturnian system, calm appearances often emerge from intricate physical interactions. Saturn's muted coloration also contributes to its tranquil visual identity. The planet displays shades of pale gold, soft beige, and subdued gray, caused by ammonia crystals and minor hydrocarbons suspended in the upper atmosphere. Spectroscopic data from Cassini's visual and infrared mapping spectrometer show that these hazes scatter sunlight in a way that smooths sharp contrasts, giving the planet its distinctly gentle glow. The absence of strong color variation underscores another scientific pattern. Atmospheres with uniform chemical composition and steady temperature profiles often exhibit low contrast banding, creating the calm, layered appearance seen on Saturn. From a physical perspective, Saturn's enormous size contrasts with its delicate density. With a radius 9 times that of Earth but only about 1/8 its density, Saturn is the least dense of all the planets in the solar system. If a sufficiently large ocean existed in space, Saturn would float. This low density reveals structural insights about the planet's composition, indicating a core surrounded by thick layers of hydrogen and helium. Models based on Cassini's gravity measurements suggest that Saturn's internal regions may host diffuse, gradually blended layers rather than sharp boundaries. This supports the broader astrophysical principle that gas giants in colder regions often develop more stable, slowly transitioning interiors. The gentle pacing of Saturn's rotation adds another characteristic to its calming identity. Saturn completes one rotation in roughly 10.5 hours, causing its equator to bulge outward due to rapid angular momentum. Despite this speed, the planet's atmosphere distributes rotational forces smoothly across latitudes. Cassini's cloud tracking experiments show that atmospheric belts accelerate and decelerate gradually, with minimal turbulence compared to the more chaotic flows found on Jupiter. This slower, steadier redistribution of energy demonstrates that a planet's rotation rate does not necessarily correlate with disruptive atmospheric behavior. Instead, internal heat and chemical composition play decisive roles in dictating overall stability. Saturn's orbit around the Sun introduces another long-term rhythm. One Saturnian year lasts approximately 29.5 Earth years, producing extended seasons that evolve over decades. Observations from the Hubble Space Telescope over multiple decades reveal these seasonal changes as gradual shifts in ring illumination, cloud reflectivity, and polar coloration. Such slow, predictable transitions reflect a system governed by gentle variations in sunlight and axial tilt. This long-term rhythm introduces the second interpretive insight. Planetary systems with slow seasonal cycles offer ideal environments for studying persistent atmospheric behavior, providing natural laboratories for observing climate stability. The first space missions to target Saturn, Pioneer 11, followed by the two Voyager spacecraft, provided initial close-range studies of its rings and magnetosphere. Their data confirmed the basic structure of Saturn's environment, but left many questions unresolved. It was not until the arrival of the Cassini-Huygens mission in 2004 that scientists gained continuous, high-resolution access to the system. Cassini's 13-year orbit provided an unprecedented timeline, allowing researchers to observe Saturn through nearly half a Saturnian year. This long observational window yielded insights into ring particle motion, atmospheric circulation, and magnetic field geometry. Such extended duration missions reveal a broader truth. In slowly evolving planetary systems, long observational baselines are essential for detecting meaningful changes. Even the magnetosphere, which can appear dynamic and storm-driven around other planets, behaves with relative steadiness around Saturn. Measurements from Cassini's magnetospheric imaging instrument show that Saturn's magnetic field is unusually symmetrical, producing well-defined boundaries that interact predictably with the solar wind. This configuration results in a magnetosphere with fewer chaotic fluctuations than those typically found around Jupiter or Earth. The calm nature of Saturn's magnetic environment supports the third interpretive insight of this section. Symmetrical magnetic systems tend to generate stable plasma interactions, which in turn support long-lived structures such as auroral ovals. As this opening section draws to its close, the viewer arrives at a structured sense of Saturn as a world defined by gradual forces. Its orbit progresses slowly, its seasons shift gently, and its atmospheric features evolve over extended timescales. Nothing in the Saturnian system moves abruptly. Instead, its changes unfold with the deliberate pacing of a cold, distant giant shaped by low solar energy and long-term gravitational equilibrium. These characteristics create an ideal foundation for the deeper exploration that follows. Saturn's shape is carved by rotation, stretched by motion, and softened by the lightness of its gaseous layers. Saturn's physical identity begins with an unusual property: its remarkably low density. With an average density of around 0.69 grams per cubic centimeter, Saturn is the least dense planet in the solar system, so light that, in principle, it would float in a sufficiently large ocean. This measurement, confirmed through decades of orbit tracking and spacecraft flybys, points to a world dominated by hydrogen and helium, with only a relatively small fraction of heavier elements. The planet's gentle buoyancy is not merely a numerical curiosity. It reveals fundamental truths about how gas giants form and evolve. Low-density planets typically contain extended envelopes of light gases that respond slowly to changing forces, establishing the overall calmness that characterizes Saturn's external behavior. Saturn's shape reflects the dynamic balance between gravity and rotation. The planet completes one rotation in approximately 10 hours and 33 minutes, making it one of the fastest spinning bodies in the solar system. This rapid rotation causes a pronounced equatorial bulge, stretching Saturn outward around its middle while flattening its poles. Cassini's precise gravity measurements demonstrated that this equatorial expansion is not superficial but extends deeply into Saturn's interior, revealing that the planet's internal material is distributed in a way that accommodates rotational forces with minimal turbulence. This supports a broader astrophysical principle. In large gas giants, rapid rotation can generate stable, predictable distortions rather than chaotic deformations. The outer layers of Saturn's atmosphere form a distinct, stratified system. The uppermost region, composed mainly of molecular hydrogen, hosts thin ammonia clouds that reflect sunlight efficiently and contribute to Saturn's pale appearance. Beneath these clouds lie deeper layers containing ammonium hydrosulfide and water ice, arranged according to temperature and pressure gradients. Observations from Cassini's imaging instruments show that these layers transition gradually, without the violent vertical mixing found on Jupiter. This gradual stratification offers the first interpretive insight of the section. Atmospheres dominated by lighter gases and lower internal heat flux tend to display smoother, more stable layering. Temperature plays a pivotal role in shaping Saturn's atmospheric structure. The upper atmosphere averages around -180 degrees Celsius, while deeper layers warm as pressure increases. Cassini's composite infrared spectrometer recorded temperature variations with exceptional accuracy, revealing that Saturn's thermal profile conforms neatly to expected gas giant models. As depth increases, the temperature rises in a near-continuous gradient, ultimately leading toward a hot, dense interior. This steady increase in temperature aligns with theoretical models of heat retained from planetary formation, suggesting that Saturn still radiates more energy than it receives from the Sun, a clue to ongoing internal processes. Beneath the visually smooth cloud tops lies a dynamically active but predictably structured weather system. Saturn's rapid rotation drives multiple east-west jet streams, some traveling faster than 1,000 kilometers per hour. Yet these jets do not produce the chaotic storms commonly seen on Jupiter. Instead, Cassini's atmospheric tracking revealed long-lived flows with consistent velocities and minimal turbulence. This supports the second interpretive insight. High-speed atmospheric motion does not necessarily generate instability. In hydrogen-rich atmospheres with low internal disturbances, jet streams can remain coherent for extended periods. Deeper still, Saturn transitions into regions where hydrogen becomes increasingly compressed. At sufficiently high pressures, approaching over 1 million times Earth's atmospheric pressure, molecular hydrogen is forced into a metallic state. This metallic hydrogen layer conducts electricity efficiently and contributes to Saturn's magnetic field. Measurements from Cassini's magnetometers showed that Saturn's magnetic axis is unusually well aligned with its rotational axis, creating a nearly symmetrical field. This alignment hints at a highly uniform metallic hydrogen layer, supporting a third interpretive insight. Symmetric magnetic fields often arise from evenly distributed conductive layers deep within gas giants. Below the metallic hydrogen region, Saturn likely hosts a diffuse core composed of rock, ice, and metallic compounds. Earlier models assumed a sharply defined core boundary, but Cassini's final gravity experiments, conducted during its grand finale orbits, suggested a more blended interior. Rather than a solid central mass, Saturn may contain a gradually mixed transition zone extending tens of thousands of kilometers outward. Such a structure helps explain why the planet responds so smoothly to rotational forces and why its density profile changes gradually with depth. These findings reinforce the modern understanding that gas giant interiors are not rigidly layered but shaped by slow mixing processes over billions of years. Saturn's physical characteristics played a role in shaping its iconic rings. While the rings are explored in later chapters, their connection to Saturn's internal structure is significant. The planet's oblate shape alters its gravitational field in subtle ways, establishing stable orbital regions where ring particles can persist. Cassini's ring mapping studies demonstrated that slight variations in Saturn's gravity influence the spacing of ring gaps and resonant features. The planet's low density and rapid rotation, therefore, have consequences not only for its own interior but also for the stability and evolution of its surrounding system. When viewed holistically, Saturn's physical profile reflects a balance among forces: gravity, rotation, pressure, and temperature. Each layer, from the upper clouds to the deep metallic interior, contributes to a coherent and predictable planetary system. Instead of abrupt transitions or chaotic boundaries, Saturn's internal structure is marked by gradual changes, slow diffusion, and long-lived stability. This overall steadiness helps explain why Saturn's external appearance is so calm and uniform, despite the fast-moving currents and enormous pressures contained within. Saturn's physical identity, shaped by light gases, rapid rotation, and a blended interior, sets the stage for deeper exploration of its meteorology and its complex atmospheric behavior. Descending into Saturn's atmosphere is entering a world without a surface, where clouds stretch downward for thousands of kilometers. Saturn's atmosphere is organized into a series of broad, continuous layers that extend far deeper than any terrestrial equivalent. The descent begins at the familiar cloud tops visible from space, where soft bands of yellow and pale gold drift in parallel strips. These colors arise from a combination of ammonia ice, suspended haze particles, and scattered sunlight. Cassini's imaging data revealed that the uppermost atmosphere consists mainly of molecular hydrogen, with trace amounts of ammonia, methane, and minor hydrocarbons. These chemicals form the foundation of a calm but complex system, where sunlight interacts with the gases to create thin layers of photochemical haze that gently tint the cloud tops. This upper region is cold, around -180 degrees Celsius, and sparse, offering the first hint of how temperature and pressure will change with increasing depth. Moving deeper, the ammonia ice cloud layer transitions gradually into zones where ammonium hydrosulfide becomes the dominant condensate. At these pressures, roughly a few bars deeper than the visible layer, ammonia reacts with trace hydrogen sulfide carried upward from warmer regions below. Cassini's spectrometers detected the presence of these compounds through specific infrared absorption features, confirming long-standing theoretical models that predicted their distribution. The smooth transition between ammonia and ammonium hydrosulfide layers provides the first interpretive insight. Saturn's atmosphere does not form abrupt discontinuities, but instead supports slow chemical gradients shaped by temperature, pressure, and atmospheric mixing. Below this zone lies an even deeper layer composed primarily of water ice and water vapor. This region is significantly warmer, with temperatures rising above -100 degrees Celsius, and pressure increasing to dozens of times Earth's atmospheric level. While water-derived clouds are hidden far below the upper decks and are not directly visible, their presence is inferred through Cassini's microwave radiometry and by comparing atmospheric models with observed thermal emissions. Water is a relatively heavy molecule compared to hydrogen or helium, so the depth of this layer offers a second interpretive insight. The deeper a compound condenses within a gas giant's atmosphere, the more massive and gravitationally influenced the surrounding environment becomes. As pressure continues to increase, Saturn's atmosphere becomes denser and more uniform. Individual cloud layers eventually dissolve into a continuous fluid envelope dominated by hydrogen and helium. The distinction between atmosphere and interior becomes progressively less meaningful. Saturn lacks a physical surface, and there is no abrupt boundary marking where the atmosphere ends. Instead, gases simply compress under their own weight, transforming gradually from a cool, stratified cloud system into warmer, thicker, and more energetic regions. Temperature climbs steadily due to gravitational compression and residual heat from Saturn's formation, eventually surpassing hundreds of degrees Celsius as depth increases. Convective motions play a key role in carrying heat outward. Cassini's thermal maps revealed that Saturn's interior releases more energy than it absorbs from the Sun, indicating ongoing internal processes such as helium rain or slow contraction. Convection occurs in large, stable cells that transport heat upward in predictable cycles. Unlike Jupiter's more turbulent weather patterns, Saturn's convection lacks sharp boundaries or frequent eruptions, contributing to the overall visual smoothness of its cloud belts. This provides a third interpretive insight. In atmospheres where internal heating is steady and rotational forces are strong, convection can form long-lived cells that maintain consistency over decades. Far below the cloud layers, pressures rise to levels where hydrogen begins transitioning from a molecular to a metallic state. This transformation occurs at pressures exceeding 1 million atmospheres, conditions unattainable on Earth but common within gas giants. While the metallic hydrogen layer lies much deeper than the atmospheric zones described earlier, it is part of the same continuous descent. Data from Cassini's gravitational field measurements suggest that these deep regions influence Saturn's rotation profile and contribute to the symmetry of its magnetic field. The gradual shift from gaseous hydrogen to metallic hydrogen highlights the extraordinary range of physical conditions present in a single planetary atmosphere. The descent into Saturn's atmosphere also explains the planet's distinctive coloration. The soft yellow and beige tones are not the result of exotic pigments, but of light scattering through haze layers and ammonia crystals. Cassini's UV imaging experiments showed how small-scale aerosols absorb higher-energy wavelengths while reflecting lower-energy light, producing the planet's characteristic pastel hues. Because the atmosphere is relatively calm and vertically ordered, these colors remain stable over long periods, with only slow variations linked to seasonal changes and upper atmospheric chemistry. Winds play a continuous but orderly role in shaping Saturn's atmospheric appearance. High-velocity jet streams sweep across the planet in alternating east-west directions, but these jets interact minimally with the layered cloud structures. Cassini tracked cloud features that persisted for years without significant deformation, demonstrating how Saturn's winds and convection coexist in a state of broad equilibrium. These observations align with established models suggesting that hydrogen-rich atmospheres, when dominated by rapid rotation and moderate internal heat, tend toward long-term stability rather than chaotic variability. A descent through Saturn's atmosphere therefore reveals a world defined not by turbulence but by continuity. Smooth transitions in pressure, chemistry, and temperature over vast vertical distances. Each layer is part of a single, unified system guided by gravitational compression, heat transport, and planetary rotation. The deeper one travels, the more Saturn's distinguishing characteristics blend into a gradual shift from cool cloud decks to high-pressure, high-temperature interior regions. Rather than a series of discrete boundaries, Saturn presents an extended continuum of physical states, illustrating how gas giants evolve and maintain structure over billions of years. This calm, layered descent provides essential context for understanding Saturn's rings. The rings interact with the planet's gravity, magnetic field, and upper atmosphere in subtle but measurable ways. Cassini observed faint interactions where ring particles in Saturn's ionosphere exchange charged particles, demonstrating that even distant features remain part of a unified system. To understand Saturn fully, we must study not only the planet, but the vast ring system surrounding it. The rings may be ancient relics or the remnants of a catastrophic breakup seen only in the quiet mathematics of orbital mechanics. Saturn's rings appear bright, stable, and timeless when viewed from a distance, but their origin remains one of the most discussed questions in planetary science. The rings are composed mostly of water ice, with particles ranging from micron-sized grains to blocks several meters wide. Their purity, brightness, and structural complexity suggest a dynamic past governed by collisions, gravitational interactions, and subtle resonances. Observations from the Cassini mission revealed that the rings are far thinner and more varied than once assumed, prompting an extended scientific debate about how this vast, delicate structure began. One leading formation theory proposes the destruction of a mid-sized moon. In this model, a former icy satellite drifted too close to Saturn and crossed the Roche limit, the distance at which tidal forces can overcome the gravitational cohesion of an orbiting body. Once inside this boundary, Saturn's gravity would have torn the moon apart, dispersing its icy crust into orbit. Over time, these fragments would spread into the thin, bright rings observed today. Cassini's density measurements of the major rings show that they contain large amounts of nearly pure water ice, supporting the idea that a moon with an icy exterior contributed heavily to their composition. This interpretation gains strength from the fact that Saturn's mid-sized moons, such as Enceladus and Tethys, are rich in similar materials. Another possibility involves the capture and disruption of a comet or icy planetesimal. Early in the solar system's history, gravitational scattering was common, sending comets inward toward the larger planets. If an object of sufficient size passed near Saturn, tidal stresses could have fragmented it, creating a temporary arc of material that later coalesced into rings. This theory accounts for the rings' relatively clean composition and for the variety of particle sizes. Cassini's ultraviolet spectrometer detected organic compounds and darker material in trace amounts across the rings, consistent with cometary origins. These components appear in low concentrations, indicating that if a comet was involved, it contributed only a portion of the total mass. A third scenario considers slower, more gradual processes. Instead of a single catastrophic breakup, the rings may have formed through steady accretion of icy debris from Saturn's ancient moons. Over billions of years, micrometeoroid impacts could have chipped away particles from moon surfaces, supplying material that drifted into stable orbital bands. This long-term accumulation model aligns with the behavior seen around smaller celestial bodies, such as Chariklo and Haumea, which host faint ring systems likely produced by repeated impacts rather than singular events. Cassini's imaging of small moonlets embedded in the rings also demonstrates ongoing accretion and erosion, suggesting that the mechanisms that maintain the rings today may resemble the processes that formed them. One of the most significant scientific questions concerns the age of the rings. For decades, the dominant view held that Saturn's rings formed early in the solar system's history, more than 4 billion years ago. This interpretation was based on the assumption that stable rings would require long time spans to develop their observed structure. However, Cassini's close-in gravity measurements, taken during its grand finale orbits, challenged this perspective. The spacecraft detected lower-than-expected mass in the rings, suggesting they may be relatively young, perhaps no more than 100 to 200 million years old. If accurate, this would imply that the rings formed during the era of the dinosaurs on Earth, a surprisingly recent event in cosmic terms. Yet, other data complicate the picture. Micrometeoroid deposition on the rings introduces dark material at measurable rates. If the rings were very young, they should appear brighter and purer than Cassini observed. Conversely, if they were very old, they should be much darker due to accumulated dust. Cassini's cosmic dust analyzer recorded a flux rate that suggests either the rings are moderately aged or that some mechanism actively cleans or recycles material. This uncertainty forms the first interpretive insight. Ring age cannot be determined solely from brightness or mass. It must be inferred through the interplay of dust accumulation, gravitational evolution, and material transport. Another interpretive insight emerges from studies of Saturn's moons. Simulations of tidal interactions indicate that the orbits of Saturn's inner moons migrate outward over time. If a moon once crossed the Roche limit due to this migration pattern, its breakup could have occurred at a relatively late stage in solar system evolution. Such a model preserves the young ring hypothesis while grounding it in the predictable physics of tidal dissipation. Cassini's measurements of Saturn's internal oscillations, detected through ring seismology, further support the idea that the gravitational environment has changed over time in ways that could lead to moon destabilization. There is also the possibility that more than one mechanism contributed to the ring's formation. A moon could have provided the bulk of the icy material, while later impacts or comet interactions added smaller contributions. This hybrid model aligns with the observed variety of particle colors, sizes, and compositions. It also explains the uneven distribution of mass across different ring regions, which likely reflects distinct sources or processes at different periods. Despite the scientific uncertainty, all models converge on a central principle. Saturn's rings are a natural outcome of gravitational physics acting on icy material in orbit. Their formation required either a single major event or a long sequence of minor ones, but in each case, the final structure is the result of stable orbital mechanics. Cassini's mission provided the clearest evidence yet that the rings are dynamic and evolving, not frozen remnants. They interact continuously with Saturn's gravity, its magnetic field, and its moons, revealing a system still shaped by ongoing processes. Therefore, the birth of Saturn's rings remains an open question, framed not by speculation but by carefully measured constraints. Whether ancient or recent, catastrophic or gradual, the rings embody a balance between destruction and accretion, one that planetary scientists continue to study using data from Cassini and ongoing simulations. Once formed, The rings evolved into a complex, dynamic system. Each ring is a river of frozen fragments, drifting in coordinated motion. To understand Saturn's rings, one must first abandon the human instinct to picture them as solid, continuous disks. Instead, imagine an immense, flattened swarm, billions upon billions of individual fragments, each fragment tracing its own orbital path around the gas giant. Together they form a shimmering tapestry, but up close, the rings dissolve into motion. Drifting snowballs, ice shards, dust grains, and the occasional embedded moonlet carving its influence through the plane. Cassini's suite of instruments, UVIS, ultraviolet imaging spectrograph, VIMS, visible and infrared mapping spectrometer, and its radio occultation experiments, allowed scientists to probe the rings with exquisite precision. What they revealed upended centuries of oversimplified assumptions. The rings are not merely made of ice, but are instead a spectrum of particle sizes, from the microscopic to the monumental. Some grains measure less than a micron across, comparable to cigarette smoke, while others are chunks the size of houses. The bulk of the mass, however, lies in centimeter to meter scale fragments. Compacted snowballs and icy boulders whose surfaces have been eroded, coated, or darkened by meteoroid dust over time. Despite the visual purity of the rings from afar, the particles are rarely pristine. Most are mixtures of water ice, trace dust, and organic molecules. Yet VIMS data show that the ice in Saturn's rings is unusually bright, far purer than typical icy moons. Much of this brightness comes from repeated surface refreshment. Collisions within the rings continually fracture and expose fresher ice, preventing the rings from darkening as quickly as untouched surfaces do. The brightness of the rings is one of their most striking qualities. Their albedo, in some places exceeding 0.9, is among the highest of any object in the solar system. Under the sun's illumination, this turns the rings into vast, reflective surfaces, creating the illusion of solidity. But the brightness is a trick of optics. Light reflects off countless flat ice facets, scattering in such a way that the rings appear almost luminescent. The pattern of light also reveals subtler truths. Regions with smaller particles reflect differently than those dominated by larger chunks. UVIS observations, for example, show enhanced ultraviolet reflectivity in certain parts of the B and A rings, a signature of purer ice. Darker bands, meanwhile, reveal the presence of embedded dust, micrometeoroids that accumulate over millions of years, gradually aging the rings. In many Cassini images, the rings appear almost satiny, as though painted by hand. But this appearance belies a constant tumult. Trillions of collisions each hour, reshaping surfaces and redistributing energy at microscopic scales. Perhaps one of the most startling discoveries from radio occultation experiments is the ring's thinness. Despite their breathtaking lateral span, over 280,000 kilometers from inner to outer edge, the main rings are rarely more than 10 to 30 meters thick. Some portions may be as thin as a two-story building. Yet the rings are not uniformly dense. Certain regions contain up to 10 times more material per square meter than their neighbors. Much of the B ring, for example, is surprisingly massive. Cassini's gravity measurements suggest it holds a significant portion of the ring's total mass. The rings behave like a fluid sheet, constantly adjusting to local variations in density and angular momentum. Edges sharpen, boundaries ripple, gaps widen or narrow. Nothing in the rings is static. Even the most well-defined structures, such as the Cassini division, are, at their core, the result of ongoing interactions rather than permanent walls. Among the billions of particles are larger bodies, moonlets ranging from a few hundred meters to several kilometers in diameter. They are not large enough to become spherical, yet they exert gravitational influence strong enough to sculpt their surroundings. Some moonlets open propeller-shaped gaps in the ring plane, two spiral arms of displaced particles trailing the tiny worldlet as it orbits. These propeller features were a triumph of Cassini's observations, revealing a hidden population of objects previously too small to detect directly. Other moonlets, such as Pan and Daphnis, True moons residing within larger gaps reshape the rings on grander scales. Their presence creates vertical waves, out-of-plane ripples that rise several kilometers before settling back into the thin sheet. Cassini observed Daphnis carving scalloped edges as sharp as a knife, pushing ring particles into delicate, curving arcs. Such interactions show that the rings are not merely debris. They are ecosystems of gravity, where every object large enough to tug on its neighbors becomes a sculptor in its own right. If one were to look closely enough, the rings would appear full of regularly spaced ripples, patterns reminiscent of vibrating sand on a drumhead. These are density waves, and they arise from resonances with Saturn's moons. When a ring particle completes an orbit in the same time it takes a moon to complete some simple fraction of its own orbit, say half or a third, a gravitational rhythm emerges. Each orbital alignment gives the particle a tiny tug. Over thousands of orbits, these tugs accumulate, forming wave-like patterns. Crests where particles bunch together and troughs where they spread apart. The A ring is particularly rich in these waves. Some resonate with Mimas, others with Enceladus or Tethys. Each wave preserves a record of that moon's influence, like grooves on an astronomical vinyl record. Even Saturn itself shapes the rings. Oscillations within the planet, essentially Saturnquakes, send gravitational pulses outward, imprinting subtle wave structures in the inner D and C rings. These so-called chronoseismology waves act as seismographs, allowing scientists to infer properties of Saturn's interior that would otherwise remain hidden. Despite their elegance, the rings are anything but stable. Particles constantly collide, exchange momentum, migrate, and shatter. Electrostatic charging, solar radiation pressure, plasma forces, and micrometeoroid impacts continually alter the composition and distribution of material. Yet somehow, from this chaos emerges an organized system. Ringlets, gaps, braids, and waves, all maintained by a delicate balance of gravity and motion. Each ring truly is a river of frozen fragments, endlessly shifting, perpetually renewed, guided by forces subtle yet grand. In the rings, gravity creates patterns as gentle as ripples and as precise as clockwork. If the composition of Saturn's rings reveals what they are made of, their dynamics reveal how they live. The rings are not a static ornament encircling a planet. They are a system, restless, responsive, and exquisitely sensitive to the gravitational choreography playing out around them. Every ripple, every gap, every razor-sharp boundary arises from the interplay of forces that repeat with clock-like precision. Saturn may be their anchor, but the moons are their sculptors, constantly reshaping the disk with invisible hands. To understand the dynamics of the rings is to witness a symphony of resonances, collisions, oscillations, and shepherding forces. What looks tranquil from a distance is, at the particle level, a storm of movement. Billions of ice fragments weaving past one another, each one obeying the same gravitational rules, each one contributing to the collective behavior of the whole. The most striking manifestations of this behavior are the density waves. These waves, first theorized in the mid-20th century and later confirmed by Voyager and Cassini, are the product of gravitational resonances. When a moon orbits Saturn at a rate that aligns periodically with the orbital speed of ring particles, say, every second, third, or fourth orbit, their gravitational pulls sync up like a repeated push on a swing. Each small tug hardly matters on its own, but over thousands of repetitions, a rhythm emerges. Particles begin to cluster into regularly spaced crests, separated by troughs where the material thins out. From afar, density waves give certain ring regions a finely ruled texture, like ripples frozen in water. Up close, they are patterns of compression and rarefaction, as if an invisible hand were strumming the rings like a harp string. Some of the strongest density waves owe their existence to Mimas, the moon responsible for clearing the Cassini division. At the inner edge of that gap lies the 2:1 resonance. Ring particles there complete two orbits in the same time Mimas completes one. Each alignment nudges them outward, gradually evacuating material and sculpting one of the most iconic features in the solar system. But Mimas's influence does not end at the Cassini division. Countless smaller resonances, scattered through the A and B rings, generate their own wave trains, spiral ripples that unwind slowly around the planet. Cassini's instruments detected more than 100 such waves, each corresponding to a specific gravitational rhythm. Resonances can also arise from within Saturn itself. Oscillations deep in the planet's interior, a kind of Saturnian equivalent of seismic pulses, send out periodic gravitational variations that imprint subtle waves in the rings. These chronoseismology waves act like stethoscopes pressed against the planet, allowing scientists to measure aspects of Saturn's internal structure, the depth of its helium rain, the size of its core, even hints of its rotation rate. Thus, the rings are more than debris. They are a recording surface for the entire Saturnian system. Yet waves and resonances are only part of the story. Another dynamic force, shepherding, creates some of the ring's most dramatic features. The term shepherd moon refers to small moons whose gravity confines ring particles into narrow bands or sharp-edged gaps. The classic example is the F-ring, a slender, braided strand perched just outside the main system. On either side of this ring orbit Prometheus and Pandora, a pair of shepherd moons whose gravitational tugs keep the F-ring tightly bound. Prometheus, the inner shepherd, periodically plunges slightly into the ring, pulling out long tendrils of material like taffy stretched between fingers. These streamers gradually curl back and dissolve into the ring's structure. Pandora, the outer shepherd, counters Prometheus's influence, keeping particles from drifting outward. Together, they maintain the ring's narrowness against the natural tendency of particles to spread over time. Cassini observed this dance repeatedly. Each close pass of Prometheus shifted the ring's core, generating kinks, knots, and temporary gaps, transient structures that made the F-ring appear alive. The ring's braided appearance emerged from this constant disruption and reorganization, a visible consequence of shepherding forces in action. Closer to the planet, the A-ring's outer edge is similarly shaped by Janus and Epimetheus, two small moons that swap orbits every few years. Their alternating gravitational influence creates scalloped boundaries, patterns that march slowly around the ring, as if painted by a rotating brush. This interplay is delicate, yet astonishingly consistent. The edge retains its integrity even as waves ripple through it. Within gaps, shepherding works in reverse. Pan, a tiny moon nestled in the Enki gap, sweeps the region clean with each orbit, maintaining a clear channel through the ring. Daphnis performs a similar role in the Keeler gap, but with a more dramatic flourish. Because Daphnis orbits slightly inclined, it kicks material above and below the ring plane, producing vertical waves, some rising as high as a kilometer. These waves curl around the gap like shock fronts, shimmering in sunlight and giving the ring edge a sculpted, scalloped form. Where shepherd moons carve order, collisions provide texture. Every particle in the rings is on a slightly different orbit, and slight differences accumulate. Over time, these variances create a circulation of energy. Particles collide and bounce, exchanging angular momentum and slowly spreading the ring material outward. Without the gravitational checks provided by Saturn's moons, the rings would gradually diffuse, smearing into a wider, less distinct disk. This spreading is counteracted by resonant boundaries, moon-driven confinement, and the ring's own self-gravity. In denser regions such as the B ring, patches of material clump temporarily into self-gravitating wakes, elongated, transient structures that form and dissolve repeatedly. These wakes influence how particles move and how light scatters through the rings, making some regions appear brighter or darker depending on viewing angle. Electrostatic forces add yet another layer. Ultraviolet sunlight charges tiny particles, causing them to levitate slightly above the main ring plane or drift along magnetic field lines. This effect is most visible in the D ring, where dusty arcs and faint, ghost-like bands shift position over months or years. Cassini watched these dusty layers rise and fall with Saturn's seasons, as solar angle and plasma environment evolved. All these processes, resonances, shepherding, collisions, self-gravity, plasma interactions, shape the dynamics of Saturn's rings. There is no single governing rule, no universal pattern. The rings are instead a network of interactions, each one influencing the others. What seems still from a distance is, in truth, a constantly reorganizing system, responding to every rhythm imposed upon it. In their dynamics, the rings reveal a profound truth about nature. Order can emerge from chaos, and complexity can arise from the simplest of forces. Gravity, acting over vast scales and subtle distances, sculpts structures that are delicate yet stable, intricate yet predictable. Beyond the rings lie worlds of their own, the moons of Saturn. Wrapped in a golden haze, Titan stands as a distant echo of early Earth, cold, quiet, and chemically rich. Titan is Saturn's largest moon and the second-largest moon in the solar system, exceeding even Mercury in diameter. Yet what makes Titan extraordinary is not its size, but its atmosphere, dense, multilayered, and chemically complex. It is the only moon with an atmosphere thick enough to obscure its surface entirely in visible light. Dominated by nitrogen, laced with methane, and wrapped in a permanent orange haze, Titan represents an environment that is both alien and structurally reminiscent of early Earth. Cassini and the Huygens lander transformed Titan from a smooth, indistinct sphere into one of the most scientifically compelling worlds in the outer solar system. Titan's atmosphere begins with a nitrogen base, comprising roughly 95% of its composition. Methane accounts for most of the remaining fraction, and its presence drives a full meteorological cycle. In this frigid environment, where surface temperatures hover near -179°C, methane behaves like water does on Earth, evaporating, condensing, forming clouds, and precipitating as rain. Cassini's spectrometers detected methane clouds drifting across Titan's poles, while its radar instrument mapped networks of channels carved by hydrocarbons. These rivers and streams drain into vast lakes and seas, particularly prominent in the northern hemisphere, where features such as Kraken Mare and Ligeia Mare form the largest liquid bodies found on any extraterrestrial surface. The surface itself, revealed in mosaics from Cassini's radar and Huygens' descent imagery, is remarkably diverse. Wide regions of Titan are covered in linear dunes composed of hydrocarbon grains, shaped by winds that shift with seasonal patterns. The dunes run for hundreds of kilometers, forming organized corridors that resemble Earth's desert landscapes, despite the radically different chemistry. These grains are thought to originate from atmospheric photolysis, where ultraviolet sunlight breaks down methane into more complex molecules that coagulate and settle to the surface as organic dust. Over geological time, winds and weather transport these grains, generating Titan's broad equatorial dune fields. Hydrology on Titan extends beyond rainfall and lakes. Cassini identified dendritic drainage systems, branching channels etched into icy terrain, suggesting episodic rainfall and surface runoff. These channels likely cut through mixtures of water ice and frozen organic compounds, which behave like rock under Titan's extreme cold. Some regions display cryovolcanic features, domes, flows, and smooth plains that might originate from subsurface reservoirs of ammonia water mixtures. Ammonia lowers the freezing point of water, allowing pockets of liquid to persist far below the surface. When buoyancy or pressure drives these liquids upward, they may erupt onto the surface as slushy flows, gradually reshaping the landscape. The Huygens probe, which descended through Titan's atmosphere in January 2005, provided the first direct observations of this alien world from within. As it passed through layers of photochemical haze, its instruments recorded temperature gradients, wind speeds, and atmospheric composition. Near the surface, the haze thickened before abruptly giving way to a clear view of icy ground. Huygens landed on a surface composed of water ice pebbles coated in organic material, evidence of erosion and transport by liquid methane. Its brief measurements confirmed the presence of methane humidity near the ground, verifying predictions made decades earlier. High above the surface, Titan's atmosphere hosts complex chemistry driven by solar radiation and Saturn's magnetospheric particles. Ultraviolet light splits methane into radicals that recombine into heavier hydrocarbons and nitriles. These molecules coagulate into aerosol particles that drift downward, gradually forming the golden smog that obscures Titan's surface. Observations from Cassini's UVIS and INMS instruments revealed a sequence of organic reactions that mirror, in broad outline, chemical pathways relevant to early Earth. Titan's upper atmosphere is thus a natural laboratory for studying prebiotic chemistry, processes that may have preceded the emergence of life on our own planet. Titan's scale adds to its significance. Orbiting Saturn at a distance of roughly 1.2 million kilometers, it sweeps through the outer regions of Saturn's magnetic environment. Its gravity is strong enough to retain its dense atmosphere for billions of years. Beneath its icy crust likely lies a global subsurface ocean, similar to those suspected on Europa and Enceladus. Tidal interactions with Saturn may provide heat sufficient to keep this ocean partially liquid. If so, Titan hosts two distinct environments of scientific interest: an organic-rich surface with methane weather, and a deep water ammonia ocean shielded beneath tens of kilometers of ice. Cassini's radar altimetry and gravity measurements strengthened the case for internal layering. Variations in rotation and shape indicated a decoupling between the crust and core, consistent with a subsurface ocean facilitating independent motion. Models suggest that Titan's interior consists of an icy shell, an ammonia-water ocean, and a rocky core with possible high-pressure ice phases between layers. These interior conditions may permit chemical gradients capable of sustaining energy-producing reactions, even at extremely low temperatures. Organic chemistry is central to Titan's scientific allure. The Moon serves as a natural experiment in atmospheric processing, sedimentation, and surface transformation. Complex molecules created in the upper atmosphere slowly drift toward the ground, where they accumulate in dunes and basins. Infrared spectra from Cassini's VIMS instrument detected a variety of hydrocarbons on the surface, including ethane, acetylene, and benzene-like compounds. Over geological time, these substances may interact with water ammonia materials from the interior, generating environments that mirror chemical conditions believed to precede life's emergence on Earth. Because of this potential, Titan has become a major target for future exploration. NASA's Dragonfly mission, a rotorcraft lander scheduled for launch in the mid-2020s, will survey Titan's dunes, organic fields, and cryovolcanic terrains. Dragonfly's ability to fly between sites offers a new perspective on Titan's diverse landscapes and surface chemistry. It will measure atmospheric conditions, analyze organic materials, and characterize the physical properties of the surface. By sampling multiple environments, Dragonfly will build a detailed picture of Titan's chemical pathways and geological processes, information essential for understanding how complex chemistry evolves in cold, distant worlds. Throughout all these observations, Titan stands as a world of contrast. It is cold but chemically active, dark yet filled with dynamic weather, familiar in process but alien in substance. Its methane seas and Earth-like cycles reveal how planetary systems can evolve along parallel tracks under entirely different conditions. Titan demonstrates that the mechanisms shaping landscapes, erosion, precipitation, deposition, and tectonic movement, are not unique to Earth but arise wherever chemistry, atmosphere, and gravity align. Even in its stillness, Titan reveals motion. Clouds rearrange with the seasons, seas rise and fall, dunes migrate inch by inch. The Moon is not frozen in geological time but participates in a slow, steady cycle driven by its unique combination of temperature, composition, and solar input. Beyond Titan's thick atmosphere, another moon holds a different but equally remarkable secret: warmth beneath the ice. Beneath Enceladus's frozen surface, warm oceans move in silence, hidden from sunlight yet rich with potential. Enceladus is one of Saturn's smallest major moons, measuring only about 500 kilometers across. Yet it possesses an interior environment of extraordinary scientific interest. What appears from a distance to be a bright, reflective sphere of ice conceals a deep global ocean beneath its surface. This ocean, warmed by tidal interactions with Saturn and enriched by hydrothermal chemistry, has elevated Enceladus to the forefront of astrobiology. Cassini's observations over more than a decade transformed this small moon from a relatively obscure object into one of the most promising locations for the search for life beyond Earth. The modern understanding of Enceladus began in 2005, when Cassini detected plumes of water vapor erupting from fractures near the moon's south pole. These jets, expelled at hundreds of meters per second, created a diffuse atmosphere around the moon and supplied fresh material to Saturn's E-ring. The source of the plumes was quickly traced to long, linear depressions called tiger stripes, named for their distinct appearance in Cassini's infrared and imaging data. These fissures are warmer than the surrounding terrain by tens of degrees, producing localized heat signatures that guided investigators toward an internal source of liquid water. Spectral analysis of the plumes revealed a mixture of water vapor, simple hydrocarbons, salts, and complex organic compounds. Cassini's ion and neutral mass spectrometer identified molecules such as methane and heavier organics, while the cosmic dust analyzer detected salt-rich ice grains that could only originate from liquid water in contact with a rocky core. Most striking were tiny silica nanograins found in the plume material, particles that form under specific hydrothermal conditions at temperatures of around 90 degrees Celsius. Their presence strongly indicates hydrothermal vents at the base of Enceladus's ocean, analogous to those found on Earth's deep seafloor. Gravity mapping provided the next major step in understanding Enceladus's interior. By measuring subtle changes in Cassini's trajectory during close flybys, scientists determined that a global subsurface ocean exists beneath an icy shell. The ice thickness varies, thinning significantly near the South Pole where the plumes erupt. This configuration suggests a dynamic system in which tidal flexing, caused by Enceladus's slightly elliptical orbit around Saturn, generates enough frictional heat to maintain liquid water. Models show that as the moon is constantly stretched and compressed by Saturn's gravity, internal stresses convert mechanical energy into heat, preventing the ocean from freezing solid. The tiger stripe fractures are central to this process. These long troughs, such as Damascus sulcus and Baghdad sulcus, serve as conduits between the ocean and the surface. Cassini's thermal infrared observations revealed that the fractures maintain temperatures far higher than the surrounding landscape, indicating sustained heat flow. Seasonal variations and changes in plume intensity suggest that the fractures widen and narrow in response to tidal forces, effectively breathing with Enceladus's orbit. During periods when the fractures widen, more material escapes into space. When they narrow, plume activity decreases. This predictable pattern reinforces the connection between tidal flexing and the moon's internal heat production. Chemical analysis of the plumes provides clues about the ocean's composition. The presence of sodium salts indicates that the ocean interacts with a rocky seafloor rather than being isolated within ice. Such interaction is critical for potential habitability, as it can create chemical gradients that support energy-yielding reactions. The detection of molecular hydrogen in the plumes, produced by water rock interactions at hydrothermal vents, suggests the presence of serpentinization, a process in which hot water reacts with minerals to produce hydrogen. On Earth, hydrogen from hydrothermal vents sustains chemosynthetic life, raising the possibility that similar processes could occur within Enceladus's ocean. Enceladus's surface features add further context to this internal activity. The south polar terrain displays few impact craters, indicating that it is geologically young. Smooth regions alternate with blocky, fractured landscapes shaped by repeated resurfacing events. Away from the pole, cratered regions of greater age suggest a quieter history, but even there, subtle tectonic features hint at long-term internal processes. Cassini's imaging revealed numerous ridges and troughs, evidence of past episodes of stress and deformation within the crust. The reflective nature of Enceladus's surface, its albedo is among the highest in the solar system, results from its continuous renewal by fine ice particles settling from the plumes. This process coats the surface in fresh frost, erasing darker regions and maintaining the moon's bright appearance. The plume's contribution to the E-ring underscores Enceladus's role within the broader Saturnian system. Although small, the moon continuously supplies material to Saturn's rings, linking the interior and exterior environments. heat flow measurements remain one of the most intriguing aspects of Enceladus. Cassini's instruments detected thermal emissions far exceeding what would be expected from radioactive decay alone. The measured heat output is consistent with tidal models but still requires efficient mechanisms to distribute and maintain internal warmth. Some models propose localized heating near the South Pole, while others suggest a global circulation of warm water beneath the crust. The precise arrangement of ice thickness, ocean depth, and heat sources continues to be refined using Cassini's extensive dataset. Because of its unique combination of liquid water, energy sources, and organic chemistry, Enceladus is considered one of the most promising environments for life beyond Earth. Its subsurface ocean is not a stagnant reservoir but a dynamic system driven by geological activity. Hydrothermal vents could supply nutrients and energy, while the ocean's contact with rock creates chemical pathways essential for prebiotic evolution. Unlike most ocean worlds, Enceladus actively transports samples from its interior to space, making it accessible for spacecraft analysis without drilling or landing. Future missions aim to build on Cassini's findings. Several mission concepts propose flying through the plumes with more advanced mass spectrometers capable of detecting amino acids, lipids, or even biological signatures. Landers or orbiters could map surface heat flow in greater detail or deploy small penetrators near the tiger stripes. These missions would deepen our understanding of Enceladus's ocean composition and test hypotheses about its hydrothermal activity. The Moon's accessibility and geophysical activity make it a compelling target for dedicated astrobiology missions. Enceladus demonstrates that habitability does not require Earth-like conditions or proximity to the Sun. Instead, it illustrates how internal energy sources and water-rock interactions can create stable, life-supporting environments deep below icy surfaces. The Moon's plumes provide a direct window into this interior, allowing researchers to study its chemistry with precision. In the broader context of planetary science, Enceladus stands as a reminder that small bodies can host complex, evolving systems shaped by gravitational forces and geological feedback. Even in its quiet orbit around Saturn, Enceladus reveals continuous internal motion, water rising through fractures, heat flowing through ice, and jets arching into space. It is a world shaped not by sunlight but by the deep, rhythmic pull of gravity and by the chemistry that unfolds where rock meets water. As these moons reveal their secrets, smaller bodies around Saturn continue to shape the planet's most iconic feature, the rings. At Saturn's pole, a perfect hexagon rotates with silent precision, an unbroken shape sculpted by atmosphere alone. Among the most astonishing features ever discovered in a planetary atmosphere is the vast, six-sided jet stream that crowns Saturn's North Pole. It is not a frozen structure, nor a cyclonic storm, nor any kind of solid formation. It is pure atmosphere, gases flowing freely, shaped by physics into a polygon that shouldn't exist, yet persists with uncanny stability. When Voyager first photographed the strange geometry in the early 1980s, scientists were stunned. Nothing in Earth's weather patterns even remotely resembles a planetary-scale shape with such clean, straight sides. And unlike transient storms that shift within hours or days, the hexagon seemed steady, almost timeless. Decades later, when the Cassini spacecraft arrived at Saturn, it became clear that this phenomenon was not only real but profoundly intricate. Cassini mapped the hexagon in exquisite detail, revealing a vast jet stream nearly 30,000 kilometers across, large enough to engulf four Earths. It encircles the pole at a latitude of about 78 degrees north, rotating counterclockwise with remarkable regularity. Inside this giant ring of motion lies a deep, swirling polar cyclone with a clearly defined eye, its eye walls towering tens of kilometers above the surrounding atmosphere. The hexagon acts as a kind of boundary around this cyclone, though the two systems are driven by different mechanisms. At its heart, the hexagon is a wave, a meandering of a high-speed jet stream embedded within Saturn's upper atmosphere. Saturn's atmosphere is dominated by hydrogen and helium, with trace gases that influence temperature and cloud composition. The planet rotates rapidly, once every 10 hours, which stretches atmospheric flows into long east-west jets. These jets are common at many latitudes, but at the North Pole, something unique happens. The jet does not form a smooth, circular band. Instead, it oscillates in latitude as it flows, generating a standing wave that produces 6 equally spaced lobes. These lobes straighten into sides because the jet stream's velocity and the planet's rotation distribute the wave energy evenly around the pole. Fluid dynamicists on Earth have reproduced similar shapes in controlled experiments. When a rotating fluid is forced to flow at different speeds in adjacent layers, polygonal patterns can form. In laboratory tanks, vortices sometimes settle into triangles, squares, or even hexagons, beautiful transient shapes emerging from simple physical principles. Saturn's hexagon is similar in concept, yet immensely larger and far more stable. It suggests that subtle gradients in Saturn's atmospheric speed and temperature create conditions that favor a permanent wave pattern. Temperature differences contribute strongly to this stability. Cassini's infrared detectors showed that the hexagon is not just visible in the clouds. It extends deep into the atmosphere. The boundaries of the hexagon mark zones where temperatures shift significantly, forming thermal gradients that help maintain the jet stream structure. Air inside the hexagon is warmer than the air immediately outside it, creating a kind of atmospheric tension that reinforces the wave pattern. Unlike storms on Earth, which rely on water vapor and solar heating, Saturn's weather is powered by internal heat, energy radiating from the planet's interior due to slow gravitational contraction. This internal heat interacts with the planet's rotation to create long-lasting atmospheric features that remain coherent for years, decades, or longer. Saturn's hexagon also displays seasonal changes. The northern hemisphere enters a long winter when it tilts away from the sun, lasting more than 7 Earth years. During this time, the pole becomes extremely cold and dark. Yet the hexagon remains. When sunlight eventually returns, it reveals subtle changes in brightness and cloud composition, but the 6-sided geometry endures, showing that sunlight is not its primary driver. The structure is deeper, likely anchored in layers of the atmosphere that remain unaffected by seasonal shading. Color also plays a role in its mystery. When first imaged by Cassini, the hexagon appeared a muted blue, possibly due to the scattering of sunlight in the cold, clear northern atmosphere. As spring approached and atmospheric haze accumulated, the hexagon shifted toward gold and honey tones. The shape never wavered, but its appearance evolved, revealing the slow dance of Saturnian seasons. The persistence of the hexagon raises an important scientific question. Why 6 sides? Why not 5 or 7? In fluid simulations, hexagons emerge as one of the most stable polygonal forms in rotating systems. They offer a balance between curvature and straightness, allowing the jet stream to oscillate without folding back on itself. If Saturn's atmospheric conditions shifted dramatically, the hexagon might deform into another shape or vanish entirely. But for at least the last several decades, and possibly much longer, the combination of wind speed, rotation, and temperature differences has kept the 6-sided wave locked into place. To planetary scientists, the hexagon offers a rare window into the deeper workings of gas giant atmospheres. It demonstrates that even in environments dominated by fluid motion, stable geometric patterns can emerge naturally. It also hints at layers of atmospheric circulation that lie far below the clouds, invisible yet essential to Saturn's weather. For viewers who enjoy planetary science and atmospheric physics, the hexagon is a marvel. A reminder that nature can produce order on colossal scales, sculpting shapes with nothing but wind and rotation. Moving away from the pole, Saturn's storms reveal themselves in cycles of immense power. Every Saturnian year, a storm forms so large it circles the entire planet in a churning belt of ammonia clouds. Among all the weather phenomena observed in the solar system, Saturn's periodic megastorms stand apart for their scale, intensity, and rhythm. Known collectively as Great White Spots, these colossal tempests erupt roughly once every Saturnian year, about 29.5 Earth years. When they appear, they transform the planet's serene bands into a sprawling, turbulent spectacle. In a matter of weeks, a single storm can grow to encircle the entire planet, stretching tens of thousands of kilometers, and rising far above the cloud layers that typically veil Saturn's deeper atmosphere. The first great white spot was recorded telescopically in 1876. Since then, astronomers have seen several more, each revealing subtle differences but following the same broad pattern. Cassini's arrival in 2004 offered the first opportunity to observe one of these events up close with modern instruments. In late 2010, the spacecraft documented the birth, expansion, and eventual dissipation of a megastorm that began as a bright plume in Saturn's northern hemisphere. Within days, the plume ballooned into a massive, spiraling convective system. It grew so large and bright that it became visible even through small backyard telescopes on Earth. The mechanics behind these storms are rooted in Saturn's atmosphere and energy balance. Unlike Earth, where surface heating from the sun drives weather, Saturn is warmed primarily from within. The planet radiates more energy than it receives, the result of slow gravitational contraction and helium rain falling toward its core. This internal heat percolates upward, interacting with the atmospheric layers composed primarily of hydrogen, helium, ammonia, and water vapor. In most latitudes, this heat emerges gently, forming the familiar alternating belts and zones. But approximately every 30 years, conditions align that allow a deep reservoir of warm, moist air to rise rapidly. The process begins far below the upper cloud decks, in the deeper water vapor layer. Over decades, this layer becomes increasingly stable, suppressing convection. Energy accumulates. Water vapor, one of the most potent drivers of atmospheric motion, remains trapped beneath colder layers of ammonia and ammonium hydrosulfide clouds. Eventually, the growing imbalance becomes unsustainable. A rise in temperature, a shift in wind shear, or a subtle change in chemical composition can trigger a sudden release. When this happens, an eruption of moist convection bursts upward, punching through the colder layers above it. Cassini's infrared spectrometers observed this process in real time. The 2010 storm's core showed enormous amounts of heat leaking upward, evidence of towering convective columns rising from deep in the atmosphere. These columns loft ammonia ice high above its usual altitude, forming the bright white clouds that give the Great White Spot its name. As these clouds spread around the planet, they feed off Saturn's rapid rotation and strong east-west winds, forming a continuous band that wraps around the globe. Once established, the storm interacts with its surroundings on enormous scales. Winds at different latitudes shear its edges, stretching the storm's structure and producing vast waves and vortices. Lightning crackles in the turbulent core, the most intense electrical activity ever recorded on Saturn. Radio emissions detected by Cassini indicated storms with flashes as powerful as those in the most intense thunderstorms on Earth, but occurring in an atmosphere far colder and composed of far lighter gases. The storm eventually destabilizes the very layer that allowed it to form. As heated material rises, it cools and spreads, releasing its energy across the upper atmosphere. Over several months, the storm consumes its deep reservoir of moisture. Without continued upward motion, the ammonia clouds dissipate. The once global band breaks apart into fragments, leaving behind chaotic wakes that slowly settle back into Saturn's normal banded pattern. One of the most intriguing discoveries came after the 2010 storm ended. Cassini found that the region affected by the storm remained cooler than expected for years. The eruption had radically altered the atmospheric structure, creating a kind of thermal scar that hinted at long-term circulation changes beneath the clouds. This suggests that megastorms are not isolated events, but are part of a broader climate cycle that shapes Saturn's atmosphere over decades. The rarity of these storms underscores how carefully synchronized Saturn's interior and atmosphere must be. Too little moisture buildup, and no storm forms. Too much wind shear, and convection is suppressed. Too much heat, and the system destabilizes prematurely. Only when these variables align every Saturnian year or so does a great white spot erupt with planetary scale force. For scientists, these megastorms offer a window into the deep atmosphere. Their size and energy reveal the presence of a dynamic internal engine. Their recurrence hints at long-term patterns in Saturn's climate. Their aftermath shows how deeply the planet's weather systems are interconnected. For viewers seeking a calm yet scientifically rich exploration of atmospheric physics, Saturn's great white spots represent a remarkable intersection of predictability and chaos. They are reminders that even in the quiet, distant outer solar system, planetary weather can unfold on extraordinary scales. Beyond these rare events, Saturn's daily weather is shaped by constant, high-speed motion. Saturn's atmosphere moves like a layered ocean, driven by rotation and shaped by temperature gradients. Saturn's weather is structured not by isolated storms alone, but by the continuous, planet-spanning circulation patterns that flow across its atmosphere. These are dominated by powerful jet streams, broad bands of east-west winds that wrap around the planet in alternating directions. Saturn's rapid rotation, completing one full spin in roughly 10 hours and 33 minutes, produces an intense Coriolis effect. This rotational influence stretches atmospheric motions into long, stable bands, preventing large convection cells from spreading poleward and instead confining them into narrow latitudinal zones. As a result, Saturn's cloud tops display a striped appearance, each band marking a different circulation regime. The strength of these jet streams is exceptional. Measurements from Cassini's imaging science subsystem and earlier Voyager tracking indicated wind speeds up to 1,800 km per hour near the equator, among the fastest sustained winds found on any planet in the solar system. Unlike Earth, where continents and topography disrupt atmospheric flow, Saturn's gaseous nature creates open pathways for winds to accelerate uninterrupted. These jets are not shallow features. Infrared and thermal observations show that they extend deep into the atmosphere, dipping far below the upper ammonia clouds and influencing the movement of materials across multiple atmospheric layers. Vertical mixing plays a critical role in shaping these bands. Saturn's atmosphere is composed primarily of hydrogen and helium, but it contains smaller fractions of methane, ammonia, and water vapor. These gases separate by altitude depending on temperature, pressure, and chemical interactions. Ammonia ice forms the highest clouds, giving Saturn its soft, pale hues. Beneath them lie ammonium hydrosulfide clouds, and deeper still, water clouds form in high-pressure regions. Jet streams move across these layers, causing upwelling in some regions and downwelling in others. Upwelling brings colder gas upward, allowing ammonia to condense, while downwelling suppresses cloud formation by warming the air and decreasing relative humidity. Cassini's composite infrared spectrometer helped quantify these motions. Thermal measurements revealed subtle temperature contrasts, sometimes only a few degrees, that correspond to jet stream boundaries. These gradients, though small, are enough to maintain stable wind bands because Saturn's atmosphere responds sensitively to thermal differences due to its low density and high rotation rate. Even minor variations in solar heating between the equator and the poles contribute to the alignment and persistence of zonal winds. One of the most notable features of Saturn's atmospheric circulation is its equatorial jet, a wide band of exceptionally fast eastward winds. This jet appears to be driven by a combination of vertical momentum transport and internal heat flow. Rising plumes from deep layers carry angular momentum upward, enhancing the eastward flow. At the same time, internal heat emerging from Saturn's interior contributes to convective turbulence that interacts with the jet. Infrared observations suggest that the equatorial jet extends thousands of kilometers deep, connecting the visible atmosphere to layers approaching the transition toward metallic hydrogen. High-latitude jets behave differently. Near the poles, jet streams become narrower and show more complex wave patterns. The most striking example is the North Polar hexagon, a stable jet stream shaped by standing waves, though similar wave activity, not necessarily hexagonal, is present in other latitudes as well. These waves indicate that Saturn's atmospheric circulation is not merely a stack of uniform bands, but a dynamic system where winds, temperature gradients, and chemical composition interact continuously. Atmospheric circulation also shapes cloud morphology. Bands of rising and sinking air determine where storms initiate and how long they persist. In regions where jet streams converge, cloud systems can accumulate and form long-lived vortices. Where they diverge, cloud cover thins, revealing deeper layers. This interplay creates Saturn's mottled textures, small ovals, stretched filaments, and subtle contrasts across its pastel-colored disk. One of the interpretive insights from Cassini's mission is that Saturn's circulation appears to be more internally driven than Jupiter's. While both gas giants radiate more heat than they receive from the Sun, Saturn's proportion of internal heat is greater relative to the energy it absorbs. This means that deeper processes, gravitational contraction, helium rain, and tidal influences from moons likely contribute more strongly to sustaining its atmospheric motion. Understanding Saturn's jets therefore offers clues not just to weather but to the planet's internal structure. Despite their strength, Saturn's winds are not static. Cassini documented gradual changes in wind speed over the years, especially near the equator. These shifts may reflect variations in heat flow, chemical composition, or interactions with large storms like the Great White Spots. Long-term monitoring from Earth-based observatories continues to refine our understanding of these patterns, suggesting that Saturn's circulation evolves over seasonal timescales spanning decades. Saturn's jet streams and atmospheric circulation reveal a world shaped by motion, from deep internal heat to the highest cloud layers traced by ammonia ice. They form the background against which storms, waves, and vortices emerge, demonstrating that even in the cold outer solar system, atmospheric physics operates with remarkable complexity. While Saturn's atmosphere evolves, human understanding of the planet has grown through centuries of observation. Through early telescopes, Saturn appeared as a world with ears, puzzling observers for generations. The human story of Saturn begins long before spacecraft and spectrometers, in an age when the planet was little more than a bright point wandering among the stars. With the invention of the telescope in the early 17th century, Saturn became one of the first planets to challenge the limits of early optics. In 1610, Galileo Galilei turned his modest refracting telescope toward the distant planet and recorded what he saw in a series of small drawings. Instead of a single round world, he observed two faint lobes beside the globe, strange appendages that he could not explain. To Galileo, Saturn resembled a three-bodied system or a planet with unusual ears. His instrument did not have the resolving power to reveal the true structure of the rings, leaving their nature open to interpretation. Over the next decades, European astronomers attempted to refine these observations. With improvements in lens grinding and telescope design, the outlines of Saturn's unusual features became sharper but still ambiguous. The physics of optics was not yet well understood, and distortions from chromatic aberration often blurred the planet's appearance. Some astronomers believed Saturn might be encircled by multiple small moons. Others suggested that the appendages were large bodies partially merged with the planet. The periodic disappearance of the rings during equinoxes only deepened the confusion. When the ring plane aligned with Earth, the thin structure virtually vanished from view, reinforcing doubts about its stability and form. A major breakthrough came in 1655 when Christian Huygens, using a more advanced refractor he built with his brother, observed Saturn with unprecedented clarity. Huygens recognized that the appendages were not separate bodies but formed a single continuous structure encircling the planet. In his notes, he described it as a thin, flat ring, a configuration unlike anything known at the time. He also discovered Titan during his observations, adding further evidence that Saturn possessed a complex system of celestial companions. Huygens' interpretation marked the first accurate description of the rings and shifted scientific understanding toward a more consistent model of Saturn's appearance. In the decades that followed, telescope makers across Europe developed longer focal lengths to reduce optical distortions. Instruments with focal lengths of 10 to 30 meters became common among dedicated observers, suspended from ropes or mounted on elaborate outdoor frames to accommodate their size. Though unwieldy, these telescopes provided improved resolution. Astronomers could distinguish the dark division within the rings, later named the Cassini division after Giovanni Domenico Cassini, who identified it in 1675. Cassini also discovered several additional moons, expanding the known structure of Saturn's satellite system and reinforcing the view that Saturn was a world of remarkable complexity. By the 18th century, Saturn had become a regular target for astronomers seeking to refine their understanding of planetary motion and celestial mechanics. Observers tracked changes in the ring tilt over time, noting how Saturn's orientation varied along its orbit. These measurements contributed to increasingly accurate models of the solar system. The development of reflecting telescopes by Isaac Newton and later by William Herschel provided new levels of clarity. Reflectors eliminated chromatic aberration altogether, giving astronomers a cleaner view of Saturn's bands, shadows, and ring structures. The 19th century saw major advances in astronomical technique. Improvements in mirror-making allowed observers to examine subtle features, including the shading of the rings and the appearance of small gaps and divisions. Photographic plates introduced a new era of documentation, capturing stable, detailed images that could be analyzed repeatedly. Saturn's rings, once sketched by hand with varying degrees of accuracy, now appeared as measurable, reproducible structures. Observers tracked storms, ring shadows, and changes in brightness across different apparitions. These data provided clues about ring composition, particle distribution, and atmospheric activity. Spectroscopy emerged as a powerful tool during the same period. By dispersing Saturn's light into its component wavelengths, astronomers detected features corresponding to hydrogen and methane in the atmosphere. Although these early spectra were limited in precision, they confirmed that Saturn was not a solid body like Earth but a gaseous world with a composition dominated by light elements. Observations of the rings suggested a different nature entirely. Their spectrum resembled that of water ice, hinting at the frozen particles that would later be confirmed by spacecraft. Through each technological advance, Saturn revealed more detail while retaining its enigmatic character. The rings, once a mysterious set of ears, became a fundamental subject in planetary science. The moons, multiplied through successive discoveries, demonstrated the planet's capacity to host a diverse set of environments. The atmosphere, studied through improved resolution and spectroscopy, showed hints of deeper processes that would later be explored in detail by space missions. Early Earth-based observation laid the foundation for all modern study of Saturn. Each improvement in optics, each new technique, and each year of careful measurement built a clearer picture of a planet far from Earth yet central to the development of planetary astronomy. What began as a puzzle seen through Galileo's refractor eventually evolved into a structured scientific narrative of rings, moons, and atmospheric dynamics. New tools would soon bring clarity. When Voyager passed Saturn, the planet transformed from speculation to detailed reality. The beginning of Saturn's modern era of exploration arrived in the late 1970s and early 1980s, when Voyager 1 and Voyager 2 swept past the planet on their grand trajectories through the outer solar system. Before these missions, Saturn was viewed primarily through Earth-based telescopes, its rings impressive, its bands faintly visible, and its moons little more than points of light. The Voyager flybys changed that perspective permanently. With cameras capable of resolving fine atmospheric structures and instruments designed to probe magnetic fields, plasma environments, and thermal signatures, the spacecraft revealed Saturn as a complex system of interconnected components. Voyager 1 made its closest approach in November 1980, transmitting high-resolution images that showed Saturn's atmosphere as a layered, dynamic world. Subtle bands and storms previously blurred by Earth's atmosphere came sharply into focus, demonstrating the fine-scale structure of jet streams and the presence of small vortices. At the same time, infrared instruments recorded temperature variations across the cloud tops, offering the first detailed thermal maps of the planet. These measurements confirmed that Saturn radiates more energy than it receives, an insight that continues to shape scientific models of its internal heat flow. The rings, long considered smooth and continuous from a distance, were revealed to be vastly more intricate than expected. Voyager imaging uncovered hundreds of ringlets, narrow gaps, and radial features. Some gaps were traced to gravitational interactions with nearby moons, while others required new explanations involving wave propagation and particle clustering. The discovery of spokes, transient, ghostly radial streaks likely created by electrostatic charging, introduced a new dimension to understanding ring physics. These features had no parallel in any other known planetary ring system at the time and demonstrated that the rings were dynamically active rather than static structures. Voyager's encounters also expanded knowledge of Saturn's moon system. Mimas, once thought to be geologically simple, displayed a large impact crater dominating its surface. Enceladus showed unexpectedly smooth terrain in some regions, hinting at internal activity that would only be fully understood decades later by Cassini. Tethys, Dione, and Rhea revealed networks of fractures and impact basins, while Iapetus displayed its striking two-tone coloration, raising questions about surface processes and material transport. The flyby measurements of Titan proved especially important. Though Voyager's cameras could not penetrate the moon's dense orange haze, infrared and radio data confirmed that Titan possessed a thick atmosphere composed primarily of nitrogen, an atmospheric profile previously unknown on any moon. Following Voyager 1, Voyager 2 passed Saturn in August 1981 from a slightly different trajectory, providing complementary views and additional data. Its images refined ring structure models and revealed even more small moons embedded within or near the rings. Voyager 2's observations of Saturn's magnetosphere, the region controlled by the planet's magnetic field, showed a magnetosphere shaped not only by solar wind but also by interactions with the rings and moons. Charged particles trapped within this magnetic environment influenced ring chemistry and contributed to the formation of transient features. Together, the Voyagers transformed the scientific landscape. They provided the first cohesive framework for understanding Saturn as a coupled system. Atmosphere, rings, moons, and magnetosphere interacting through gravity, radiation, and plasma processes. The data they returned shaped research for decades and highlighted key mysteries that later missions would focus on, including the age of the rings, the depth of atmospheric jet streams, and the geological activity on moons such as Enceladus and Titan. Voyager imagery also shifted public perception. Saturn, once a distant point of curiosity, appeared as a world with texture, structure, and complexity. Images of the rings, interlaced, sculpted, and glowing against the planet's shadow, became iconic representations of planetary beauty. The spacecraft, continuing their journey beyond Saturn, left behind a legacy that extended well beyond their technical lifetimes. For viewers seeking a calm but detailed narrative of planetary exploration, the Voyager missions represent a turning point where observational astronomy merged with robotic presence, and long-standing questions gained new clarity. The flybys did not offer complete answers, but they revealed enough to redefine scientific priority and inspire the next generation of missions. This progress set the stage for the most influential mission of all. Through early telescopes, Saturn appeared as a world with ears, puzzling observers for generations. For much of recorded history, Saturn was simply a faint, wandering point of light, slow, pale, and distant. Ancient observers recognized its unusual steadiness and its long orbital period, but without optical aid, it remained a featureless star in the night sky. This began to change in the early 17th century with the invention of the telescope. Although primitive by modern standards, early refractors altered humanity's view of the heavens, and Saturn became one of their most intriguing subjects. In 1610, Galileo Galilei turned his telescope toward the planet and recorded a sight that defied interpretation. Instead of a round disk, Saturn appeared elongated, with two strange protrusions on either side. Galileo described them as ears, unable to resolve the rings due to the limitations of his instrument. Over subsequent years, these appendages seemed to vanish and reappear as Saturn moved through different orbital positions. Without understanding ring geometry, Galileo believed the planet might consist of three bodies or that the shape itself was changing. His observations were accurate, but the explanation remained out of reach. A clearer interpretation arrived decades later. In 1655, Dutch astronomer Christian Huygens used a more refined telescope equipped with better lenses and a longer focal length. With these improvements, Saturn's shape became clearer, and Huygens realized the planet was surrounded by a thin, flat ring. He proposed that the ring was detached from the planet and did not touch its surface, an insight remarkable for its accuracy. He also discovered Titan the same year, detecting the moon's slow movement over several nights. Throughout the late 17th and early 18th centuries, astronomers continued refining their understanding of Saturn's rings. Giovanni Domenico Cassini, director of the Paris Observatory, identified a major division within the rings, now known as the Cassini division, marking the separation between the A and B rings. His observations laid the groundwork for understanding ring structure as a system of separate components, not a single uniform sheet. As optics improved, so did the ability to track Saturn's changing appearance. Observers noted seasonal variations, including the periodic dimming and brightening of the rings as Earth crossed the plane of the ring system. During these moments, the rings seemed to disappear entirely, becoming invisible in Earth-based telescopes. Such observations confirmed their extreme thinness and provided early measurements of inclination and orientation. By the 19th century, telescope craftsmanship reached new heights. The work of William Herschel and later William Lassell expanded the known family of Saturnian moons. Herschel discovered Mimas and Enceladus in 1789, while Lassell added Hyperion in 1848. Each discovery revealed a solar system far richer and more diverse than previously imagined. Saturn's moons, once invisible to the naked eye, emerged as worlds of their own. Spectroscopy in the late 1800s allowed astronomers to begin analyzing Saturn's atmospheric composition. By spreading planetary light into a spectrum, scientists detected signatures of ammonia and methane, confirming Saturn as a gas-rich world rather than a solid body. This marked a turning point. Saturn was no longer just a distant curiosity. It was a physical place governed by chemical and physical laws accessible to study. By the early 20th century, Earth-based astronomy provided a fairly complete outline of Saturn's basic characteristics. Its rings, its largest moons, its rotation, and its atmospheric composition. Yet much remained unknown. The rings' origin was unclear. The internal structure of Saturn was speculative. The fine-scale behavior of storms and atmospheric bands was invisible through even the largest telescopes. And the smaller moons, many embedded within the ring system, remained undiscovered. Still, the groundwork was laid. From Galileo's confusion to Huygens' clarity, from Cassini's ring division to Herschel's moon discoveries, humanity had begun piecing together a world so distant that light itself took more than an hour to arrive. New tools would soon bring clarity. When Voyager passed Saturn, the planet transformed from speculation to detailed reality. The space age dramatically expanded humanity's understanding of Saturn. After centuries of relying on Earth-based telescopes, the opportunity to send instruments directly into the outer solar system offered a transformative leap forward. This new era began in 1979, when NASA's Pioneer 11 became the first spacecraft to fly past Saturn. Although its instruments were limited by today's standards, Pioneer provided the first close-range measurements of the planet's magnetic field and ring environment. It confirmed the presence of a complex magnetosphere, identified new moons, and captured the earliest close-up images of the ring's structure. The real turning point came with the twin Voyager missions. Voyager 1 flew past Saturn in November 1980. Its imaging systems revealed unprecedented detail in the rings, exposing fine structure, gravitational waves, and subtle variations in brightness. The spacecraft discovered several new moons, including Atlas, Prometheus, Pandora, and Epimetheus, many orbiting near or within the ring system. Voyager 1 also provided the first close images of Titan, detecting its thick haze but unable to penetrate it, leaving the moon's surface hidden. Voyager 2, arriving in August 1981, performed a complimentary flyby, refining measurements and capturing views of Saturn's southern hemisphere. It mapped atmospheric bands, observed storms, and traced the motion of the equatorial jet. Its radioscience experiments measured ring particle density and thickness, revealing just how thin the rings truly are, sometimes only tens of meters deep despite stretching hundreds of thousands of kilometers outward. Together, the Voyagers transformed Saturn from a distant disk into a complex planetary system. They demonstrated that the rings were dynamic rather than static, shaped by countless gravitational interactions. They revealed moons with diverse geologies. They provided precise measurements of mass, density, and magnetic field strength. And they showed that Saturn's atmosphere was far more active than ground-based observations had ever suggested. Voyager's success reshaped scientific priorities. Saturn was no longer viewed merely as a gas giant with picturesque rings, but as a multi-moon environment demanding deeper exploration. The flybys also exposed the limitations of brief encounters. To understand Saturn in detail, scientists needed a spacecraft that could stay, observe, and adapt over time. That realization set the stage for a new mission, one that would orbit Saturn for more than a decade and deliver the most comprehensive view ever obtained of a planet other than Earth. This progress set the stage for the most influential mission of all. For 13 years, Cassini drifted around Saturn, watching seasons change and worlds reveal themselves. The Cassini-Huygens mission stands as one of the most ambitious planetary explorations ever undertaken. Launched in 1997 and arriving at Saturn in 2004, Cassini orbited the planet for 13 years, gathering an extensive dataset that transformed every aspect of Saturnian science. Its suite of instruments, ranging from high-resolution cameras to plasma detectors, spectrometers, and radar imaging systems, provided a continuous view of Saturn, its rings, and its moons across nearly half a Saturnian year. Cassini's arrival marked the first time a spacecraft entered stable orbit around Saturn. From this vantage point, the mission documented the planet's seasonal shifts, tracing changes in atmospheric bands, temperature gradients, and cloud patterns. Its cameras captured the evolution of storms, the persistence of the North Polar hexagon, and the shifting colors of the hemispheres as sunlight migrated from one pole to the other. The mission's discoveries extended far beyond Saturn itself. Radar data revealed Titan's surface in remarkable detail. Lakes, dunes, drainage channels, and cryovolcanic features previously hidden beneath its orange haze. Atmospheric measurements showed a methane-based hydrological cycle with parallels to Earth's water cycle. This investigation culminated in the Huygens probe, which detached from Cassini and descended onto Titan's surface in January 2005. Its landing provided the first direct observations from the surface of a world beyond Mars. Cassini also transformed understanding of Enceladus. Early gravity data hinted at internal complexity, but in 2005, the spacecraft captured images of plumes erupting from the Moon's south pole. Later flybys sampled these plumes directly, detecting water vapor, organic molecules, salts, and silica grains, evidence for a global subsurface ocean with hydrothermal activity. This discovery reshaped the search for habitable environments in the solar system. The rings themselves became a major focus of the mission. Cassini measured their particle composition, mapped density waves, and documented the influence of shepherd moons with unprecedented clarity. Its radio and stellar occultations revealed microstructure within the rings, fine-scale clumping, self-gravity wakes, and complex wave patterns shaped by moon resonances. During the mission's final phase, Cassini executed a series of grand finale dives between Saturn and its rings, measuring gravitational fields that helped determine ring mass and refine theories about their age. Over 13 years, Cassini collected more than 450,000 images and a vast archive of spectral and gravitational data. The mission ended in September 2017, when the spacecraft entered Saturn's atmosphere to prevent contamination of moons that might harbor life. As it fell, Cassini continued transmitting measurements until contact was lost. Its legacy is profound. A complete, evolving portrait of a planetary system rich with geological, chemical, and atmospheric complexity. As Cassini mapped ring structures, deeper gravitational interactions came into focus. In Saturn's rings, faint waves act as an echo of vibrations deep within the planet. Saturn's rings are not simply collections of ice orbiting in predictable circular paths. Hidden within their delicate structure are patterns, ripples, waves, and subtle undulations that act as sensitive seismographs for the planet itself. These features, mapped in extraordinary detail by Cassini, reveal that Saturn's interior generates oscillations strong enough to imprint themselves onto the surrounding ring system. Through this connection, scientists have gained a new window into the planet's internal structure, using the rings as a natural detector of gravitational harmonics. The basis of this phenomenon lies in Saturn's internal oscillations, rhythmic motions within the planet caused by density variations and dynamic processes deep below the cloud layers. These oscillations slightly alter Saturn's gravitational field. Though these changes are extremely small, the rings respond with measurable precision. Just as sound waves create patterns on a vibrating surface, Saturn's gravity produces spiral density waves throughout the rings, especially in the dense and finely structured C ring. Cassini's data allowed scientists to identify these waves as a form of ring seismology, an emerging field that uses the rings to probe the interiors of gas giants. When the spacecraft conducted radio and stellar occultations, passing starlight or radio signals through ring material, scientists saw repeated signatures that matched theoretical models of Saturn's internal modes. These modes behave like pulsing spherical harmonics, revealing how different layers inside Saturn shift and move. The rings translate these motions into organized wave structures, providing a measurable link between the planet's deep interior and its visible surroundings. One of the most significant interpretations from this research is the nature of Saturn's core. The gravitational harmonics suggest a core that is not sharply bounded but instead diffuse, an extended region of rock, ice, and metallic hydrogen blending gradually over thousands of kilometers. This challenges earlier assumptions of a compact, well-defined core like those found in terrestrial planets. Instead, Saturn may contain a fuzzy interior shaped by millions of years of mixing, with density slopes that ripple outward and influence its gravitational field. The rings reveal more than just the presence of a layered core. Cassini's measurements showed that the gravitational harmonics correspond to multiple oscillation modes, each associated with different depths. Some waves indicate shallower density variations, likely influenced by helium rain or changes in convection patterns. Others correspond to deeper modes originating near the boundary between metallic hydrogen and molecular hydrogen layers. These insights are only possible because the rings serve as amplifiers, translating weak gravitational variations into visible, measurable patterns. Spiral density waves caused by these oscillations are distinct from those generated by moons. While moon-driven waves appear at predictable orbital resonances, internal seismic waves form at unexpected locations, often deep in the C ring. Cassini's images revealed finely spaced spirals, too small to be caused by any satellite. Their spacing and structure correspond to the oscillation frequencies inside Saturn, confirming that they originate from internal gravitational variations rather than external bodies. Ring seismology also highlights the remarkable sensitivity of the C ring. Its sparse distribution of particles allows small gravitational shifts to propagate without being overwhelmed by collisions or dense material. In contrast, denser rings like the A and B rings dampen such signals, making them harder to detect. This selective sensitivity helps scientists map how oscillations of different wavelengths interact with various parts of the ring system. These gravitational harmonics demonstrate that Saturn's rings are not passive structures, but dynamically engaged components of the planet's larger system. Their particles constantly respond to the gravitational field, adjusting position and velocity in ways that preserve the shape of the waves. Over long periods, these harmonics can subtly redistribute ring material, although the effects are far less dramatic than those caused by moons or meteoroid impacts. Still, they highlight a continuous, gentle interaction between Saturn's interior and its rings, a connection spanning tens of thousands of kilometers. Cassini's gravity science experiments further refined these interpretations. By tracking small changes in the spacecraft's trajectory during close flybys, researchers measured minute variations in Saturn's gravitational field. When combined with ring wave analysis, the data formed a coherent picture of the planet's internal structure. This synergy marked one of the most scientifically productive aspects of Cassini's mission, demonstrating how multiple observation methods can converge to reveal processes far below the visible atmosphere. The study of gravitational harmonics continues to evolve. Current models use the ring wave patterns to explore whether Saturn's internal layers rotate at different speeds, a phenomenon known as differential rotation. Early evidence suggests that rotation deep inside the planet may not match the atmospheric rotation rates, hinting at more complex internal dynamics. Such insights are invaluable, not only for understanding Saturn but also for developing broader models of gas giant evolution in other planetary systems. Through the gentle patterns etched in the rings, Saturn communicates the motions hidden within its vast interior. These faint waves, detectable only through meticulous measurement and careful interpretation, reveal the planet's internal rhythm, a steady oscillation maintained over geological timescales. External forces also shape the rings. Across the rings, gaps form not from emptiness, but from rhythmic gravitational interaction. Saturn's rings appear calm and unbroken from a distance, but their structure is organized by a complex network of orbital resonances, gravitational rhythms that shape where particles can and cannot remain. These resonances occur when ring particles orbit Saturn at a speed that forms a simple ratio with the orbit of a nearby moon. Even though the moon may be hundreds of thousands of kilometers away, its repeated gravitational tugs accumulate over time, clearing material from specific regions and sculpting the rings into the patterns observed today. The most well-known example is the Cassini division, the broad, dark gap between the A and B rings. This region is governed by a 2:1 orbital resonance with Mimas, one of Saturn's mid-sized moons. Ring particles located within the division orbit Saturn twice for every single orbit completed by Mimas. At each alignment, Mimas exerts a gravitational pull. Individually, these tugs are gentle, but their cumulative effect destabilizes particle orbits. Over thousands of years, material is gradually pushed away from the region, leaving behind a low-density zone that became visible through telescopes long before the physics behind it was understood. Cassini's orbital profiles and stellar occultation measurements confirmed that the Cassini division is not empty but contains thin strands of ring material and faint density waves. These features testify to the delicate balance between orbital motion and the continuous influence of Mimas. The resonance does not remove all particles. Instead, it maintains a dynamic equilibrium in which most material is expelled while small traces survive in stable niches. This structure illustrates how resonances create order without producing perfectly sharp boundaries. Other moons contribute similarly. Enceladus, Janus, Epimetheus, and Prometheus all establish resonant zones linked to the narrow ringlets between Saturn's major rings. The Encke and Keeler gaps within the A ring are maintained by embedded moons Pan and Daphnis, but their edges are also influenced by resonant effects from more distant satellites. Cassini's high-resolution imaging revealed that these gaps are bordered by spiral waves, alternating compression and expansion zones caused by repeated gravitational forcing. These waves propagate outward like ripples, demonstrating how resonances transmit energy across the ring system. Not all resonances clear gaps. Some create bands of enhanced density by crowding particles into narrow regions. These are seen as faint ringlets, stabilized by orbital rhythms rather than expelled by them. Cassini's edge-tracking instruments showed that these ringlets often shift slightly over time, responding to minute changes in moon orbits. Such variations are caused by tidal interactions and long-term orbital evolution within the Saturnian system. Resonances thus become tools for probing the slow migration of moons, offering clues about Saturn's interior and the distribution of its mass. Resonances also operate in 3 dimensions. Some force particles to oscillate vertically, lifting them above or below the ring plane. In these cases, the resonance imparts a periodic inclination, creating vertical waves. Cassini detected these waves through stellar occultations, where the apparent brightness of background stars flickered as ring particles passed in front. Vertical waves move more slowly than radial ones because they involve motion out of the ring plane. Their presence indicates that resonances do not merely shape the surface structure of the rings, but influence their full spatial geometry. A critical insight from Cassini's radio and ultraviolet occultations is that resonances propagate over long distances. A moon can influence ring material much farther from its orbit than early models predicted. This results from the extreme sensitivity of Saturn's ring particles to gravitational disturbance. Composed primarily of water ice, these particles experience low drag and very little collisional damping, allowing resonant energy to travel efficiently through the system. The rings therefore act as a responsive medium, amplifying small perturbations into observable structures. Resonances evolve over time. As moons shift slowly outward due to tidal interactions with Saturn, their resonant positions drift as well. Gaps and waves migrate with them, causing subtle long-term changes in ring architecture. Cassini documented these drifts across its 13-year mission, providing evidence that the ring system is not static but slowly reconfiguring. This dynamism helps researchers understand the timescales of ring evolution and the internal properties of the Saturnian system, including how energy is exchanged between the planet and its moons. Orbital resonances also interact with ring self-gravity. In regions of higher density, particle-particle attraction can counteract resonant forcing, allowing material to remain in marginally unstable locations. This interplay creates the sharp, intricate structures visible in the A and B rings. Self-gravity wakes, elongated clumps of particles, align with resonant directions, producing textures that Cassini imaged in unprecedented detail. The combination of moon influence and particle self-interaction forms a dual mechanism that governs where structures sharpen and where they disperse. These principles extend beyond Saturn. Orbital resonances shape asteroid belt gaps, lock Jupiter's Galilean moons into stable orbits, and influence the architecture of exoplanet systems. The rings provide a scaled, highly visible example of how gravitational rhythms guide matter into patterns across the universe. Studying Saturn's resonances, therefore, contributes to a broader understanding of orbital mechanics, from planetary formation to long-term system stability. In Saturn's rings, orbital resonances operate as a quiet, continuous force. They sculpt, organize, and maintain gaps and boundaries with precision that emerges naturally from repeated gravitational interaction. Far from chaotic, the system behaves like a coordinated arrangement shaped by rhythm rather than violence. These forces guide the evolution of the rings over time. Though bright today, Saturn's rings are slowly fading, grain by grain. Saturn's rings, often imagined as permanent celestial structures, are in fact temporary expressions of a delicate balance between gravity, sunlight, and the gradual erosion of icy material. They appear immense and luminous through telescopes, yet their long-term evolution reveals a system in transition. Cassini's final measurements, gathered during its grand finale dives, showed that the rings are losing material at a measurable rate, slow, but steady on geological timescales. This decay shapes Saturn's future appearance, marking the rings not as static ornaments, but as evolving participants in the planet's larger history. The rings consist primarily of water ice, ranging from dust-sized grains to blocks several meters wide. Their brightness reflects this youthfulness. Clean, unweathered ice produces high albedo, giving the rings their iconic shine. Over time, however, micrometeoroid bombardment steadily darkens and erodes the particles. Interplanetary dust constantly sweeps through Saturn's orbit, striking ring particles at high speed. Each impact fractures the ice, generating fine debris and coating particles with darker, carbon-rich material. Cassini's cosmic dust analyzer measured the flux and composition of this incoming material, showing that even small amounts of dust can dramatically change ring appearance over millions of years. Ring decay is driven by more than external impacts. Solar ultraviolet radiation and charged particles trapped in Saturn's magnetic field slowly modify the ice chemically, a process called radiolytic weathering. Over long periods, these reactions alter surface compositions, reducing reflectivity. The most dramatic effect, however, comes from a process known as ring rain, the continuous drift of ice and dust into Saturn's upper atmosphere. Cassini's ion and neutral mass spectrometer detected water group ion streaming along magnetic field lines, confirming that the rings are shedding material directly onto the planet. This ring rain occurs when ultraviolet light charges ring particles, giving them an electrical interaction with Saturn's magnetosphere. Charged particles become coupled to magnetic field lines and migrate inward, ultimately entering the atmosphere. Once there, they break into molecular fragments that alter chemical balances in Saturn's ionosphere. Estimates from Cassini's final orbits suggest the rings may lose hundreds to thousands of kilograms of material per second. Although small compared to the ring's total mass, this continuous loss indicates that their current brightness represents a relatively short-lived stage. Another contributor to long-term evolution is viscous spreading. The countless collisions between particles gradually redistribute angular momentum throughout the ring system. Over millions of years, this causes some ring material to drift inward while other portions drift outward. Material moving outward becomes more diffuse, while material moving inward gradually spirals closer to Saturn, eventually merging into the upper atmosphere or forming transient ringlets. Computer simulations of the process, supported by Cassini's high-resolution imaging, show that viscous spreading drives the slow but inevitable expansion and thinning of the entire ring system. All these processes raise a fundamental question. How old are Saturn's rings? Early theories suggested they were ancient, possibly as old as the solar system itself. But Cassini's observations challenged this view. The ring's brightness implies relatively little darkening from dust accumulation, pointing to a younger age. Dynamical models of ring decay suggest the rings might be only 100 to 200 million years old recent on cosmic scales. Yet uncertainties remain. Saturn's gravity and magnetic environment may redistribute material in ways that obscure true age estimates. Some researchers argue that periodic resurfacing of ring particles through collisions may keep them looking young even if the rings are older. The scientific debate remains active, highlighting how the rings continue to surprise despite centuries of observation. Regardless of their origin, the long-term trend is clear. Saturn's rings are slowly diminishing. Over the next few tens of millions of years, the main rings will likely become thinner, darker, and more diffuse. The A and B rings may persist the longest due to their larger mass, while the fainter C and D rings will fade sooner. The E ring, maintained by Enceladus's geysers, will evolve according to changes in plume activity. Ultimately, the rings could dissipate entirely, leaving Saturn looking more like Jupiter. An elegant world of bands, vortices, and subtle atmospheric patterns, but without its familiar luminous halo. For scientists, studying this evolution is essential to understanding not only Saturn, but also the dynamics of disks across the universe. Rings represent scaled-down models of protoplanetary disks and accretion systems. Their slow transformation reveals how gravity, collisions, and radiation shape orbiting material over time. Each wave pattern and each drifting grain reflects broader physical laws that govern planetary formation and loss. Saturn's rings today appear serene and enduring, but their future is one of gradual change. They stand at a moment in cosmic history when they are bright enough to study in detail, yet transient enough to remind us that even seemingly stable astronomical structures evolve across time. Their fading is not a disappearance, but a continuation of the same processes that shaped them: accretion, erosion, spreading, and descent. The rings may fade, but Saturn itself has a deeper internal life. Deep beneath Saturn's atmosphere lies a core shaped by pressure no experiment on Earth can replicate. Saturn's internal structure begins in a region far beyond direct observation, where pressures rise to millions of atmospheres and temperatures exceed 10,000 degrees Celsius. In this extreme environment, matter behaves in ways not found naturally on Earth, forming a dense central region that scientists describe as Saturn's core. Models built from Cassini's gravity measurements suggest that this core is not a sharply defined solid sphere but a broad, diffuse region composed of heavy elements, rock, metals, and ices, mixed with hydrogen under immense pressure. Estimates place the core's mass at roughly 10 to 20 times that of Earth, though its boundary blends gradually into the layers above it. The existence and size of Saturn's core provide clues about how the planet formed. Planetary formation simulations indicate that a core of heavy materials must have accumulated first, sweeping up solid particles and icy fragments in the early solar system. Once this core reached several Earth masses, it would have begun attracting hydrogen and helium from the surrounding protoplanetary disk, growing rapidly into the gas giant observed today. Cassini's data supported this model, revealing gravitational signatures consistent with a heavy element interior that remained distributed through deeper layers due to slow mixing over billions of years. Pressures in the core exceed those found anywhere except the hearts of larger gas giants. Under such compression, materials lose familiar properties. Water becomes superionic, forming a crystalline lattice of oxygen with hydrogen ions moving freely through it. Rock becomes partially dissolved, merging with metallic hydrogen in a fluid-like mixture that carries heat outward. These extreme phases cannot be replicated fully in laboratories, though high-pressure experiments using Diamond-Ville cells provide partial analogs. To bridge the gaps, researchers rely on computer simulations that model the behavior of matter at millions of atmospheres, helping interpret Saturn's observed gravitational field. One of the most significant insights came from Cassini's grand finale orbits. As the spacecraft flew repeatedly between Saturn and its rings, subtle variations in its trajectory revealed new details about the planet's internal mass distribution. These measurements suggest that Saturn's core is not sharply defined but diluted, extending outward across a large fraction of the planet's radius. Instead of a compact central sphere, Saturn likely contains a gradually changing mixture of heavy materials and hydrogen, with no strict boundary separating solid and fluid phases. This result reshaped earlier models and brought Saturn closer to the category of a fuzzy or mixed-core giant. The amount of heat emerging from this deep interior drives much of Saturn's atmospheric circulation. Internal energy escapes slowly toward the upper layers, influencing the formation of jet streams, storms, and long-term weather cycles. The behavior of the core may also contribute to internal oscillations, gravitational modes that extend through the planet and imprint subtle wave patterns onto the rings. These waves function like seismological readings, allowing scientists to infer internal conditions without direct measurement. Interpretive models show that the core continues to evolve even today. Over time, helium droplets formed in deeper layers may rain downward toward the center, releasing additional heat and contributing to Saturn's internal luminosity. This process affects the layering of materials and may help explain why Saturn radiates significantly more energy than it receives from the Sun. The slow descent of helium enriches the core and alters its density structure, an effect Cassini's gravity measurements were sensitive enough to detect. Saturn's core remains one of the most challenging planetary environments to understand because no instrument has ever directly sensed its conditions. Yet, through gravitational modeling, high-pressure physics, and long-term observations, scientists have begun reconstructing its composition and behavior with increasing confidence. Each new dataset, whether from Cassini, ground-based spectroscopy, or interior simulations, refines the picture of a deep, compressed world where matter transitions gradually into exotic states. Saturn's internal story begins here, in a region defined not by solid ground but by extreme physics. Its core anchors the planet, shaping everything from formation history to atmospheric motion. Above the core, matter enters a new state. In extreme pressure, hydrogen becomes metallic, carrying electric currents that generate Saturn's magnetic field. Saturn's interior transitions gradually from molecular hydrogen near the cloud tops to deeper, denser layers where pressures exceed anything achievable in Earth-based laboratories. Beneath the outer envelope, hydrogen, normally the simplest and most abundant element in the universe, undergoes a profound transformation. At depths where pressures rise into the millions of atmospheres and temperatures exceed several thousand degrees Celsius, hydrogen is compressed into a metallic state. In this form, electrons move freely, enabling the fluid to conduct electricity much like a molten metal. This electrically conductive layer is essential to Saturn's magnetic and thermal behavior. Measurements from the Cassini mission refined the understanding of this transition zone. As the spacecraft performed close gravitational flybys during its grand finale orbits, scientists analyzed slight perturbations in Saturn's gravity field. These variations helped infer changes in density deep within the planet, offering clues to how thick the metallic hydrogen layer might be and how sharply it is differentiated from the overlying molecular hydrogen. Data from Cassini's magnetometer also provided insight. Saturn's magnetic field is unusually axisymmetric. Its magnetic poles are almost perfectly aligned with its rotational axis. This symmetry suggests that the dynamo responsible for the field operates within a spherical region where electrical conductivity remains high and convection remains vigorous. In the metallic hydrogen layer, convection drives powerful internal currents. Hotter material rises, cooler material sinks, and the resulting motion interacts with the planet's rotation. This process generates Saturn's magnetic field through a geodynamo mechanism similar in principle to Earth's, though operating under far more extreme conditions. Because hydrogen in this layer behaves as a conductive fluid, it can maintain currents large enough to sustain the magnetic field we detect from space. Cassini's grand finale orbits revealed that this field extends deep into the planet and remains stable over long timescales, indicating a dynamo that is both efficient and enduring. One interpretive insight emerging from Cassini data is that Saturn's metallic hydrogen region appears thicker relative to the planet's size than Jupiter's. Although Saturn is less massive overall, the pressure needed to create metallic hydrogen can exist over a broader interior zone because the planet's density decreases more gradually with depth. This suggests that Saturn's interior structure may be more diffuse, with a softer gradient between the molecular and metallic layers. Some models propose a fuzzy core, where heavy elements dissolve into the metallic hydrogen over time, creating a transitional region rather than a distinct boundary. Thermal processes within this layer also influence Saturn's observable atmosphere. As helium separates out of the hydrogen mixture under extreme pressures, droplets may form and sink toward the deeper interior. This helium rain releases heat, contributing to Saturn's internal energy output. Observations from Cassini's infrared instruments indicate that Saturn emits significantly more energy than it receives from the Sun, a sign that processes deep within the metallic hydrogen layer are active contributors to the planet's thermal budget. This excess heat helps drive convection in the upper atmosphere, shaping the jet streams, storms, and banded patterns visible at the cloud tops. The metallic hydrogen region likely rotates at a different rate than the layers above it. Because Saturn lacks a solid surface, determining the true rotation period is challenging. Researchers have relied on measurements of the magnetic field and ring seismology data, which track oscillations in the rings linked to internal vibrations. These observations suggest that the metallic hydrogen layer behaves as a coherent, rotating shell that influences the planet's overall rotation signature. Subtle differences between the rotation of this deep layer and the overlying atmosphere help explain variations seen in Saturn's radio emissions. Chemical components within the metallic hydrogen region remain difficult to analyze directly, but theoretical models propose that it may contain dissolved heavier elements, such as oxygen, silicon, or carbon compounds, delivered during the planet's formation. These elements, once part of a primordial core, may gradually diffuse outward under the intense pressures and temperatures. This process influences Saturn's density distribution, affecting gravity measurements and shaping the structure of the metallic hydrogen region. Understanding this layer is essential for interpreting Saturn's magnetic characteristics. The nearly perfect symmetry of the field puzzled scientists for years. Planetary dynamos often produce tilted magnetic axes, as seen with Earth and Jupiter. Saturn's alignment suggests either a unique dynamo configuration or a stabilizing mechanism within the metallic hydrogen region. Some models propose that the overlying molecular layer acts as a filter that smooths the field, while others suggest that the dynamo operates deeper than previously assumed, in a region where rotation is more uniform. Despite these insights, the metallic hydrogen region remains one of the least directly observable parts of Saturn. Its properties must be inferred from gravitational, magnetic, and seismic data. Yet each line of evidence supports the view that this layer is one of the planet's defining features. Energetic, electrically active, and central to Saturn's behavior as a gas giant. Heat produced within Saturn fuels what we observe above. Saturn emits more heat than it receives, a quiet glow from internal contraction. Saturn's internal heat is one of the defining characteristics of the planet's long-term evolution. While it sits far from the Sun, receiving only about 1% of the sunlight that reaches Earth, it radiates significantly more energy back into space than it absorbs. This surplus comes from internal processes, most notably slow gravitational contraction. Saturn continues to shrink very gradually over time, and as it contracts, potential energy is released and converted into heat. This mechanism, known as the Kelvin-Helmholtz process, has been operating since the planet's formation and remains a major source of its internal luminosity. Cassini's composite infrared spectrometer measured Saturn's outgoing thermal radiation, confirming that the planet gives off roughly twice as much energy as it receives. These observations help constrain models of Saturn's interior, because the distribution of heat affects convection, atmospheric motion, and long-term structural changes. Unlike Jupiter, Saturn exhibits an additional complication: the presence of helium rain. Over billions of years, helium droplets are believed to have separated from the planet's hydrogen-rich upper layers and sunk deeper toward the interior. As these droplets fall, they release gravitational energy, contributing further to the heat budget. This helium rain likely explains why Saturn emits more heat than Jupiter relative to their sizes and masses. Measurements of helium abundance in Saturn's upper atmosphere, lower than expected in equilibrium conditions, support the idea that helium continues to migrate downward. The boundary between the metallic hydrogen layer and the molecular hydrogen envelope is thought to be a region where these droplets accumulate and dissolve, releasing energy slowly and steadily. Cassini's gravity data reinforced the idea of a layered interior where such differentiation processes can occur over long timescales. Internal heat influences atmospheric dynamics as well. Saturn's powerful jet streams, large-scale circulation patterns, and episodic megastorms all depend on the upward transport of heat. Energy from the deep interior rises through the molecular hydrogen layer, interacts with cloud-forming regions, and shapes the temperature gradients that define the belts and zones visible from space. The thermal structure of the atmosphere, mapped by Cassini over many years, shows that seasonal changes alone cannot account for the observed variations in temperature. Instead, much of the complexity seen in Saturn's weather is tied to the slow, persistent release of planetary heat. This heat also affects the planet's long-term evolution. As Saturn continues to cool and contract, its internal structure may change, altering the balance between molecular and metallic hydrogen and gradually shifting the depth of convection zones. Models predict a slow decrease in emitted energy over billions of years, but the exact timeline remains uncertain because the rate of helium separation is still an active research topic. Cassini's end-of-mission atmospheric plunge provided valuable data on density and composition that continue to refine these evolutionary models. The quiet glow of Saturn's internal heat represents more than an atmospheric driver. It is a record of the planet's formation and the physical processes that have shaped it since the early solar system. Observations across the infrared spectrum highlight how far Saturn remains from thermodynamic equilibrium, still releasing the energy of its birth and slowly adjusting to the conditions of deep time. Even at its immense age, the planet is not static. Its interior continues to evolve, and that evolution subtly influences everything above, from the rings to the jet streams. This internal activity influences Saturn's position within the greater solar system. Saturn's orbit forms part of the solar system's outer architecture, balancing gravitational influences across billions of kilometers. Among the planets of the outer solar system, Saturn occupies a position that is both structurally stabilizing and dynamically active. Orbiting the Sun at an average distance of 9.5 astronomical units, Saturn lies within a region where solar radiation is weak, orbital periods lengthen into decades, and gravitational interactions extend across vast spatial scales. Its placement defines part of the solar system's broader architecture. Interior to the ice giants but exterior to Jupiter, the system's most massive planet. Saturn's orbit, nearly circular with only a mild eccentricity, contributes to long-term stability among the giant planets by avoiding major resonances that could otherwise shift or destabilize their paths over millions of years. The dynamical interplay between Saturn and Jupiter is especially important. Their combined gravitational fields impose subtle variations on each other's orbits, creating slow oscillations in eccentricity and inclination. These cycles unfold over timescales of tens of thousands of years and are known from orbital simulations that integrate planetary motion over geologic epochs. Despite these interactions, Saturn's orbit remains predictably stable. This stability allows the planet to maintain a consistent role in shaping the structure of the solar system's outer regions. From the viewpoint of celestial mechanics, Saturn is not merely one of many planets. It is a gravitational participant that influences the long-term dynamics of multiple small body populations. Saturn's orbital period of 29.5 Earth years shapes the seasonal cycles of its atmosphere and rings, but it also influences the timing of certain resonant patterns among objects sharing its general orbital region. While Saturn does not host a large population of co-orbital bodies, its gravitational field interacts indirectly with objects located much farther away. In particular, it plays a measurable role in the dynamical behavior of the asteroid belt. Periodic gravitational alignments between Saturn, Jupiter, and the asteroid belt create regions known as Kirkwood gaps, zones cleared by orbital resonances. Although Jupiter is the primary driver, Saturn's gravitational pull subtly modulates the strength of these resonances. Models that remove Saturn from simulations show that the distribution of asteroids becomes noticeably altered, demonstrating the planet's contribution to sculpting interior populations despite its great distance from them. In the outer solar system, Saturn also influences the Centaur objects, a population of icy bodies orbiting between Jupiter and Neptune. These objects follow unstable orbits that evolve due to gravitational encounters with the giant planets. Saturn acts as both a deflector and a conveyor, altering the paths of passing centaurs and occasionally redirecting them toward Jupiter or outward toward Uranus. Statistical studies of centaur dynamics show that Saturn plays a significant role in determining their short-term and long-term evolution, guiding some toward temporary orbital capture and others toward ejection from the outer solar system. Saturn's orbital configuration also appears to contribute to the overall stability of the outer planetary system by damping large-scale perturbations. Because the giant planets exert mutual gravitational pulls, the system behaves like a collection of interacting oscillators. A slight shift in one orbit can influence others, but Saturn's relatively moderate mass and distance produce stabilizing effects rather than disruptive ones. Dynamical simulations demonstrate that Saturn helps prevent Jupiter's orbit from drifting into more eccentric configurations. This stabilizing influence has implications for the long-term climate conditions on Earth and the inner planets, as the overall structure of the solar system affects the flux of comets, asteroids, and dust reaching the inner regions. Saturn's slow movement through space also contributes to resonance networks that extend across the solar system. These networks include gravitational interactions that are not immediately visible but accumulate over millions of years. For example, Saturn's orbit affects the long-term evolution of objects in the Kuiper belt, not through direct gravitational influence. Its distance is far too great, but through resonance chains transmitted via Jupiter, Uranus, and Neptune. These connections illustrate how Saturn participates in a multilayered gravitational system, one in which each planet influences others through a hierarchy of interactions. The calm, regular path of Saturn around the Sun also produces subtle changes in the distribution of interplanetary dust. Dust particles migrating inward due to solar radiation forces encounter gravitational perturbations from Saturn, which can trap them in resonant orbits or scatter them outward. Observations from Cassini's cosmic dust analyzer provided evidence that some dust populations near Saturn have been partially shaped by these long-range interactions. Though these effects are small, they demonstrate how Saturn contributes to the continuous redistribution of material across the solar system. Saturn's orbital role is therefore both local and extended. Locally, it governs the dynamics of its moons and rings. Regionally, it influences small body populations in the vicinity of the giant planets. And globally, it participates in the long-term architecture of the solar system. Its orbit is a bridge between the inner giant planets and the more distant ice giants, forming part of a larger gravitational structure that has persisted for billions of years. Its mass also shapes nearby populations. Saturn's gravitational field directs the dance of dozens of moons and countless ring particles. Saturn functions as a gravitational anchor for one of the most complex satellite systems in the solar system. Across its vast sphere of influence, forces operate with precision, guiding the paths of moons both large and small, while shaping the subtle structures within the rings. These interactions are not static. They unfold continuously, revealing a system that evolves through resonances, tidal forces, and exchanges of angular momentum. Each component, from Titan down to the smallest icy grain, responds to Saturn's gravitational field in predictable but intricate ways, forming a dynamic environment observed in detail by spacecraft such as Cassini. Understanding these interactions provides insight into how multibody systems behave across planetary systems and highlights the processes that organize Saturn's extensive family of orbiting worlds. Many of Saturn's moons orbit in resonant relationships, where their orbital periods form simple numerical ratios. These resonances lock motions into long-term stability while also transferring energy between bodies. For instance, Tethys and Mimas occupy a 2:1 resonance, meaning Mimas completes 2 orbits for every one made by Tethys. This steady gravitational rhythm modifies their orbital eccentricities and helps sustain features such as Mimas's slight internal heating. Similar resonances shape the orbits of Dione and Enceladus. In Enceladus's case, it's 2:1 resonance with Dione forces periodic stretching and compression that generates the heat powering its subsurface ocean. These examples show how Saturn's gravity not only positions its moons but influences their geological activity. The rings respond to resonances as well. The Cassini division, a broad gap between the A and B rings, is maintained largely by a 2:1 resonance with Mimas. Particles attempting to orbit within this region are repeatedly perturbed, preventing stable orbits from forming. Other, more subtle gaps correspond to weaker resonances involving additional moons. These gravitational connections create the distinct banded structure visible in high-resolution images. In this way, rings reflect the hidden geometry of Saturn's satellite system, tracing the orbital mathematics that defines the region. Saturn's larger moons also exert influences across the ring plane. Titan, with its substantial mass and distant orbit, produces a gentle but persistent gravitational pull that shapes long-term evolution. Over millions of years, Titan's outward migration, caused by tidal interactions with Saturn, affects the positions of other moons and gradually shifts resonant boundaries. Cassini's precise tracking measurements revealed that Titan is moving outward faster than previously estimated, suggesting a more efficient transfer of energy within Saturn's interior. This behavior has implications for the entire satellite system, potentially altering ring interactions over geological timescales. Closer to the rings, small moons act as immediate sculptors. Prometheus and Pandora, the shepherd moons of the F-ring, confine its particles within a narrow path. Their alternating gravitational tugs stretch and compress the ring, creating braided patterns and temporary streamers. Pan and Daphnis, embedded within the A-ring, maintain sharp-edged gaps through repeated gravitational clearing. As these moons orbit, they produce waves in nearby particle streams, some vertical, some radial, revealing how even kilometer-scale bodies contribute to the system's structure. Cassini's imaging documented these effects in detail, showing how small shifts in a moon's orbit can generate visible disturbances that propagate outward through the ring material. Saturn's gravity also influences the internal behavior of moons. Tidal forces knead Enceladus's ice shell, shape Titan's atmospheric circulation through orbital eccentricity, and likely contribute to the internal structures of Rhea, Dione, and other mid-sized satellites. Cassini's gravity science experiments measured subtle distortions during flybys, offering clues about interior oceans, differentiated cores, and variations in ice thickness. These interactions demonstrate that the moons are not isolated bodies but participants in an interconnected system with Saturn at its gravitational center. Ring particles themselves undergo constant motion influenced by both Saturn and the moons. Collisions between particles redistribute angular momentum, while gravitational interactions maintain spiral density waves that ripple across the rings. Radio occultation experiments conducted by Cassini revealed how these density waves correspond directly to moon positions. As moons migrate or shift slightly due to tidal interactions, the locations and strengths of these waves change accordingly. This creates a feedback loop in which the rings serve as sensitive detectors of small changes within the satellite system. Beyond their immediate dynamics, the moons and rings help shape Saturn's magnetosphere. Charged particles released from Enceladus's plumes feed into Saturn's magnetic environment, forming a torus of material that interacts with magnetic field lines. This plasma environment influences ring particle charging and contributes to the removal or deposition of material on ring surfaces. Thus, gravitational and electromagnetic systems overlap, linking deep interior processes on Enceladus with the outermost layers of Saturn's atmospheric and magnetic structure. Long-term observations show that Saturn's system is evolving. Tidal dissipation within Saturn causes gradual outward migration of moons, potentially altering resonant relationships. Micrometeoroid impacts darken the rings and contribute to slow mass loss. These changes illustrate how gravitational interactions extend beyond immediate motion to guide the future of the system. Saturn's gravitational influence extends across thousands of kilometers, guiding moons, shaping rings, and driving internal processes. It creates a dynamic environment where stability and change coexist. Understanding these interactions offers insight not only into Saturn but into how complex systems behave around planets throughout the galaxy. These dynamics continue into the distant future. Despite its size and complexity, Saturn maintains orbital stability over billions of years. Saturn's long-term stability is shaped by the balance of forces that govern its orbit around the Sun. Its path is nearly circular, with a modest eccentricity that keeps its distance from the Sun within a relatively narrow range. This circularity reduces gravitational stress on the planet and its moons, helping preserve the orbital architecture that has existed since the early solar system. Saturn completes one orbit every 29.5 Earth years, moving at a speed slow enough that solar perturbations act gradually, allowing its position and momentum to remain stable on timescales far beyond human history. Its mass, second only to Jupiter, creates a large gravitational sphere of influence that helps anchor its orbital behavior within the solar system's broader structure. Gravitational interactions with Jupiter are the primary external influence on Saturn's long-term orbital evolution. The two gas giants are locked in a slow-moving gravitational relationship, exchanging angular momentum in a way that produces small but measurable oscillations in their orbits. These oscillations occur over tens of thousands of years, forming part of the broader dynamical cycles that shape the outer solar system. Numerical simulations indicate that while these interactions introduce subtle shifts in orbital inclination and eccentricity, they remain within ranges that preserve long-term stability. Saturn's orbit is therefore not static but dynamically consistent, evolving without drifting into chaotic behavior. Saturn's moons also contribute to its long-term orbital equilibrium. The combined gravitational pull of Titan, Rhea, and the mid-sized moons adds internal structure to the Saturnian system, distributing angular momentum and moderating the planet's axial tilt. Titan, with its large mass and tidal interactions, exerts a gentle but persistent torque on Saturn. These internal gravitational exchanges help prevent Saturn's tilt from varying rapidly, preserving the seasonal rhythm observed during Cassini's 13-year mission. Over geologic timescales, these interactions maintain order within the system, ensuring that Saturn's internal gravitational balance aligns with the planet's orbital environment. One of the most significant contributors to Saturn's stability is its relatively low axial precession rate. Compared with terrestrial planets, whose axes can wobble significantly due to uneven mass distribution, Saturn's internal structure and rotation create a strong stabilizing moment. This reduces long-term variations in obliquity, preventing large-scale climate shifts that might otherwise influence the upper atmosphere. The result is a stable seasonal cycle that repeats consistently over hundreds of orbits, with gradual changes traceable through infrared and ultraviolet observations spanning decades. Solar tides, though weak at Saturn's distance, introduce gradual changes in orbital parameters. These shifts unfold over millions of years and are incorporated into models of solar system evolution. The consensus emerging from long-term dynamical simulations is that Saturn's orbit remains secure far into the future. Even as the Sun slowly evolves on its path toward the red giant phase billions of years from now, Saturn's distance will allow it to survive the expansion of the solar atmosphere, though its environment will change dramatically. Saturn's stability is therefore not a simple consequence of its mass or distance but the result of interlocking gravitational relationships, balancing internal dynamics, solar perturbations, and the influence of Jupiter. Through these relationships, Saturn maintains a predictable path, quietly tracing its orbit through space while contributing to the structural integrity of the outer solar system. Yet nothing in the cosmos is unchanged forever. Saturn's rings are evaporating into space, falling into the planet as a fine rain. Saturn's rings appear timeless, yet every measurement indicates that they are temporary structures, bright, delicate, and ultimately short-lived on cosmic timescales. What looks like a permanent feature is, in reality, a transient phase in Saturn's long planetary history. Observations from Cassini, combined with Earth-based infrared and radio measurements, reveal that the rings are slowly but steadily disappearing through a process known as ring rain. Over tens of millions of years, the ice that forms the rings is drifting inward, pulled by Saturn's gravity, depleted by micrometeoroid bombardment, and lost to atmospheric absorption. The first hints of ring loss emerged from early Voyager data, which showed faint ultraviolet emissions in Saturn's upper atmosphere. Decades later, Cassini measurements confirmed that these emissions were caused by charged water molecules from the rings entering the atmosphere along magnetic field lines. This process delivers water vapor, oxygen ions, and small particles into Saturn's ionosphere, altering its chemical balance. Cassini's INMS instrument detected this inflow directly during its final orbits, measuring thousands of kilograms of material falling into Saturn every second. Though this rate fluctuates across regions, the combined effect suggests that the main rings may dissipate in roughly 100 to 300 million years. Micrometeoroid bombardment accelerates this decline. The rings are composed primarily of bright water ice, up to 95% pure in some regions. Over time, dust from interplanetary space collides with these ice particles, darkening them and reducing their reflectivity. This gradual soiling increases the rate at which radiation pressure and plasma interactions pull material inward. Cassini's cosmic dust analyzer recorded these impacts, showing that even the smallest grains contribute to the slow erosion of the ring system. The process is gentle at any given moment, but persistent across millions of years. Tidal interactions also play a role. Saturn's rings exist within the planet's Roche limit, where tidal forces prevent large bodies from coalescing into moons. Instead, particles continually collide, fragment, and redistribute. While this maintains the ring's broad structure, it also slowly grinds material into smaller grains. The smallest grains are most easily influenced by Saturn's magnetic field and by solar radiation pressure, causing them to spiral inward. Over long intervals, the combined effect resembles a slow inward cascade, a steady migration from sweeping arcs of icy debris to diffuse haze and eventual disappearance. One of Cassini's most important findings was the variation in ring mass. Using gravity measurements during its grand finale orbits, the spacecraft mapped the internal structure of Saturn and simultaneously tracked the gravitational influence of the rings. These readings showed that the rings are less massive than previously believed. Lower mass implies faster decay, because there is less material to resist the ongoing processes of erosion, bombardment, and plasma drag. The A and B rings, the brightest and most substantial, dominate the total mass. Even so, their measured density aligns with a system that is young and slowly thinning. Interpretive insights suggest that Saturn's rings are not only fading but likely formed relatively recently, perhaps within the last 100 million years. The high reflectivity of the ice implies limited exposure to dust and radiation. A ring system billions of years old would be significantly darker. This has led to renewed interest in formation theories involving the breakup of a moon or the disruption of a comet. Whatever their origin, the rings appear to be a temporary stage rather than a permanent architectural feature of Saturn. As the rings recede, they will not vanish all at once. The D ring, closest to Saturn, will continue thinning first, followed by the tenuous edges of the C ring. The major rings will gradually lose their structure, with gaps widening, edges blurring, and particle populations shifting toward smaller sizes. Eventually, the remnants will exist only as faint, diffuse arcs detectable primarily through infrared or radio instrumentation. Long after that, only subtle signatures in Saturn's upper atmosphere may reveal that a grand ring system once existed. For viewers seeking a calm, scientific perspective, the fading of Saturn's rings illustrates the dynamic nature of planetary systems. Even features that appear serene and unchanging are shaped by slow processes acting over vast timescales. The ring's disappearance is not a dramatic event, but a quiet transformation, unfolding grain by grain over millions of years. As the rings fade, Saturn will continue its long evolution. Over millions of years, Saturn's atmosphere will cool further as the Sun changes. Saturn's long-term evolution is shaped by slow processes, orbital dynamics, thermal decline, and the gradual transformation of the Sun. Unlike the rapid atmospheric motion visible today, the future of Saturn unfolds across millions to billions of years, governed by predictable astrophysical principles. As the solar system ages, the flow of heat, light, and gravitational interactions will shift, creating subtle but measurable changes in the planet's environment. In this section, the narration traces these calm, drawn-out transitions, grounded in models of planetary cooling and stellar evolution. At present, Saturn emits more energy than it receives from the Sun, powered by gradual gravitational contraction and helium separation within its interior. Over immense spans of time, this internal heat will continue to diminish. Planetary cooling models suggest that Saturn's effective temperature, already only about 95 Kelvin, will fall further as internal reserves dissipate. As heat output decreases, convective activity within the deep atmosphere will weaken, leading to reduced vertical mixing between layers. Cloud structures may become more stable, with fewer large convective upwellings or major storms. Ammonia ice clouds could grow thinner as the temperature gradient between atmospheric layers becomes more uniform. The Sun's evolution also plays a central role in Saturn's distant future. Stellar models indicate that as the Sun ages, it gradually brightens, increasing its luminosity by roughly 10% every billion years. Although Saturn lies nearly 10 times farther from the Sun than Earth, even small increases in solar output have measurable consequences. Over millions of years, the slow rise in sunlight will slightly warm Saturn's upper atmosphere while its interior continues to cool. This opposing trend, warming above, cooling below, will alter temperature contrasts that currently drive zonal winds. Jet streams may slow as gradients weaken, especially in the equatorial region where wind speeds are most sensitive to thermal structure. Saturn's orbit itself remains broadly stable over long timescales, but subtle variations accumulate over millions of years. Influences from Jupiter's gravity cause periodic changes in Saturn's orbital eccentricity and inclination. These secular variations shift the distribution of solar heating across the planet, modulating seasonal contrasts. Cassini's long-term observations revealed that Saturn's atmosphere already responds to modest orbital changes. In the far future, as these cycles continue, seasonal patterns may grow more pronounced or more subdued depending on the alignment of orbital parameters. Interactions with the moons also influence Saturn's evolution, particularly through tidal forces. Over immense timescales, tidal dissipation gradually alters the orbits of several major moons, especially Titan. Models suggest that Titan is slowly migrating outward due to tidal interactions. As Titan moves farther away, its gravitational influence on Saturn's atmosphere and magnetosphere will change. Tidal heating within Saturn's interior may decline slightly as gravitational exchanges decrease, further contributing to long-term cooling. The outward migration of moons also affects gravitational resonances that shape ring and moon system dynamics, though these changes occur on timescales far beyond human observation. Another long-term shift arises from Saturn's magnetic field. Generated within the metallic hydrogen layer, the field depends on internal heat-driven convection. As Saturn cools, the vigor of this convection may decrease. Over hundreds of millions of years, the magnetic field could weaken or reorganize, subtly altering the flow of charged particles around the planet and affecting auroral patterns at the poles. Observations from the Hubble Space Telescope and Cassini's ultraviolet instruments show that auroral intensity already varies with solar activity. In the distant future, reduced magnetic strength would further influence these interactions. Eventually, the Sun will enter its red giant phase, drastically altering conditions throughout the solar system. Although Saturn lies far beyond the region that will be engulfed, the Sun's expanded luminosity will bathe the outer planets in significantly stronger light. Saturn's upper atmosphere will warm, while the planet's interior continues to contract slowly. Chemical processes in the atmosphere may shift as ultraviolet radiation increases. Methane, ammonia, and other molecules sensitive to photochemical reactions will respond to stronger solar irradiation, potentially altering the appearance of the cloud tops. Yet these changes will still unfold against a backdrop of gradual cooling and fading internal heat. Saturn will become a colder, more quiescent world, its storms softer, its jets slower, and its contrasts gentler. The overall structure of the planet will remain intact, but its atmospheric activity will evolve in step with the changing energy environment of the solar system. Eventually, even the solar system itself evolves. Saturn stands as a reminder of cosmic scale, slow, persistent, and quietly magnificent. Across centuries of observation, Saturn has carried a unique place in human imagination. It is neither the largest world nor the closest, yet its presence evokes a calm sense of order in the vastness of the solar system. Much of this impression arises from its visual character, a pale, muted sphere embedded within an elegant system of rings. Even through small telescopes, Saturn appears composed, balanced, and serene. In this stillness, observers sense a kind of cosmic patience, an object that evolves on timescales far beyond the rhythms of daily life on Earth. This perception aligns with the nature of the planet itself. Saturn rotates rapidly, but its storms tend to unfold slowly. Its rings swirl in precise orbits, shaped by gentle gravitational interactions rather than abrupt collisions. The moons beyond the rings move in steady, predictable paths, echoing the long-term stability of the planet's orbit. These elements form a portrait of motion without haste, of dynamical structures that shift subtly over years, decades, and centuries. For viewers who seek scientific calm, Saturn embodies a universe governed not by sudden events, but by gradual, understandable processes. Observational history reinforces this impression. Early astronomers Huygens, Cassini, Herschel spent years sketching the planet, tracking the quiet variations in its rings and atmospheric patterns. Their work was defined not by dramatic discoveries but by the quiet accumulation of detail. Through these observations, Saturn became a symbol of the scientific method, a world that reveals itself slowly, rewarding patience and precision. In this way, Saturn's calmness is not only planetary but also conceptual. It teaches that understanding grows through consistent attention, through the willingness to observe without expectation. Modern spacecraft continued this tradition. Voyager's flybys brought clarity, but it was Cassini's long orbit that shaped contemporary understanding. 13 years of continuous observation provided a real-time example of Saturn's patient nature. Storms forming gradually, rings shifting subtly, seasons transitioning at a pace measured in Earth decades. From these observations emerged insights that could not have been obtained through brief encounters. The quiet persistence of the planet required an equally patient observer. Cassini's mission became a reflection of Saturn itself, methodical, deliberate, and oriented toward long-term understanding. Saturn's atmosphere reinforces this theme. Though capable of producing some of the largest storms in the solar system, most of its motion is defined by steady jet streams and enduring patterns. The hexagon at the North Pole, with its geometric regularity, illustrates how order can emerge from fluid motion under stable conditions. Infrared measurements show that these structures persist season after season, sustained by consistent temperature gradients and rotational dynamics. Even the changes that do occur, brightness variations, wind shifts, or seasonal cloud patterns, unfold in slow arcs, demonstrating a type of atmospheric behavior shaped by long timescales and deep internal heat. On larger scales, Saturn represents calm persistence within the architecture of the solar system. Its orbit helps maintain dynamical balance among outer planets and influences long-term stability of small body populations. While interactions occur, resonances, gravitational nudges, slow exchanges of angular momentum, they do so over millions of years. Saturn's gravitational role is not one of disruption, but of guiding and moderating. In this way, Saturn embodies a broader cosmic principle. Systems evolve not only through rapid change, but through subtle, continuous interactions that accumulate gradually. From a reflective perspective, Saturn encourages a shift away from short-term thinking. Observing the planet, whether through a telescope, spacecraft data, or detailed models, requires an appreciation of scale. Storms may last only weeks, but cycles span decades. Ring evolution unfolds over tens of millions of years. Internal heat dissipates over billions. These timescales invite viewers to consider the deep rhythms of the cosmos, cycles that exceed human lifetimes yet remain governed by physics that can be observed, measured, and understood. In this sense, Saturn's calmness is not emptiness or inactivity. It is a demonstration of productive stillness, of motion that conveys coherence rather than chaos. The planet illustrates how vast systems maintain structure through balance, between rotation and gravity, between internal heat and atmospheric loss, between moon interactions and ring evolution. Each component fits into a broader dynamical pattern that operates without haste and without interruption. For many viewers, this is the deeper reason Saturn remains compelling. Its scientific qualities, complex rings, internal structure, atmospheric physics, are intrinsically fascinating. Yet beyond these details lies a broader impression. Saturn as a symbol of the universe's ability to maintain order across immense distances and times. It encourages reflection not through spectacle, but through the quiet assurance that cosmic systems follow laws that can be traced, predicted, and appreciated. Through observation, we find meaning not in drama, but in detail. To watch Saturn is to witness time move at a gentler pace. Observing Saturn invites a shift in perspective, a widening of the mind toward scales measured not in hours or days, but in seasons, orbits, and epochs. Through telescopes, spacecraft, and patient accumulation of knowledge, Saturn becomes a model for how slow observation reveals depth. Its atmosphere evolves gradually, its storms reappear in cycles measured in decades, and its rings transform over spans far longer than a human lifetime. In the calmness of its motion, the planet demonstrates that understanding the cosmos often begins not with rapid discovery, but with steady, repeated attention. Every layer of Saturn's system rewards this patience. The rings, seemingly static at first glance, reveal intricate dynamics only when viewed over long periods. Embedded moonlets drift minutely, sculpting edges and carving narrow gaps. Density waves ripple outward from gravitational resonances, changing subtly as the orbits of moons evolve. This is motion on a slow scale, measured in centimeters per second, yet shaping structures tens of thousands of kilometers across. Observers studying Saturn learn to appreciate processes that unfold gradually, guided by predictable physics and long-term interactions. Saturn's atmosphere offers similar lessons. Its jet streams maintain form over decades, preserving patterns that persist through seasonal sunlight changes. The powerful equatorial jet, the polar hexagon, and the alternating bands form a circulation system shaped by rotation, internal heat, and chemistry. Yet within this stability lies variation. Temperature gradients shift with the solar cycle. Storm systems emerge and fade. Hazes accumulate and disperse. To detect these trends requires ongoing observation, emphasizing how planetary science builds through cumulative measurement rather than single moments. Space missions have strengthened this perspective. Voyager's brief encounters provided a snapshot, revealing structure and diversity that reshaped scientific understanding. Cassini, circling Saturn for 13 years, instead offered a chronicle. It watched cloud patterns change with the seasons, monitored the growth of a megastorm from its earliest plume, tracked atmospheric heating in solstice light, and followed the evolution of rings, auroras, and moon interactions. This long-term observation showed that Saturn is neither static nor chaotic. It is a system governed by continuous, measurable change. The calm pacing of its environment encourages a similar pacing in scientific interpretation. Through Saturn, the value of patience in astronomy becomes clear. Most processes in the solar system are slow, and only long-duration studies reveal their full character. The faint drift of ring material, the tidal exchange between moons, the gradual cooling of the atmosphere, and the slow inward migration of particles, all become visible only when decades of data are combined. Saturn teaches that cosmic understanding rarely arrives all at once, but grows step by step as measurements accumulate. For observers on Earth, Saturn also encourages a quiet form of reflection. This predictable return to the night sky each year invites recurring attention. Amateur astronomers trace its movement among constellations, observe ring tilt angles change with orbital geometry, and witness storms or unusual features when they appear. Professional observatories monitor seasonal transitions in ultraviolet and infrared wavelengths, each dataset adding to long-term records that reveal subtle climatic cycles. In both cases, the act of observation becomes a form of continuity, connecting distant events to gradual personal experience. Saturn offers perspective not only through motion and change, but also through scale. The size of its atmosphere, the depth of its cloud layers, and the vastness of its rings remind viewers that natural processes can operate on dimensions far beyond those of everyday life. Recognizing these scales encourages a calm, outward-looking mindset, one that acknowledges the immensity of the universe while grounding understanding in measurable, physical principles. Saturn's predictable orbit around the Sun, maintained over billions of years, becomes a symbol of stability within cosmic evolution. At the same time, its system's fragility becomes apparent through careful study. The rings, though bright and expansive, are temporary. Their gradual loss into Saturn's atmosphere reveals the slow impermanence even within large structures. The moon Enceladus, continuously venting material into space, shows how delicate mechanical balances sustain long-term geological activity. Titan's methane cycle hints at an atmosphere in transition. Observers learn that persistence and change coexist in every planetary system, and that insight emerges from tracking both across time. Saturn's overall message, conveyed through decades of observation, is that understanding the universe requires balance. Patience reveals slow processes, precise measurement reveals underlying physics, and continued observation reveals long-term evolution. Through this balance, Saturn becomes more than a distant planet. It becomes a reference point for quiet exploration, demonstrating how careful study transforms distant phenomena into coherent scientific knowledge. With this calm reflection, the documentary closes by returning the viewer to the present moment, where Saturn continues its orbit, unchanged in its grandeur yet always offering new details to those who watch patiently. If you found comfort or clarity in this quiet journey through Saturn's realm, consider supporting the channel. A simple like helps this documentary reach others who enjoy calm, science-based exploration. Subscribing ensures you won't miss future long-form deep dives into the cosmos. And if you'd like to see more worlds, more mysteries, or more slow explorations of the universe, feel free to share your suggestions in the comments. Thank you for spending this time in Saturn's orbit. Until our next journey, may the stars remain steady above you.